Look up at the night sky. You see the pinpricks of light, the familiar constellations, maybe even the faint haze of the Milky Way. It feels peaceful, known, almost like an old friend. But what if I told you that this serene view is hiding a secret? That everything we learned in school, those tidy diagrams of the solar system and the basic facts about stars, is just the tiniest, most simplified introduction to a reality so bizarre and magnificent it would defy belief. Our universe is not the calm, orderly place it appears to be. It is a cosmic stage for events of unimaginable power, mysteries that challenge our very understanding of physics, and wonders that remain hidden from standard textbooks. Think you have a pretty good grasp on space? Prepare to have your mind completely rewired. Today, we are going on a journey far beyond the classroom to uncover 30 astonishing space facts that you almost certainly never learned in school. This isn't about memorizing the names of Jupiter's moons or the order of the planets. This is about the hidden layers of reality, the diamonds raining from the sky on distant worlds, the silent, invisible giants wandering between stars, the echoes of creation itself still ringing through the vacuum. We are about to pull back the curtain on a cosmos that is infinitely more strange, more violent, and more beautiful than you ever imagined. Each fact is a doorway into a deeper mystery, a piece of a puzzle that scientists are still desperately trying to solve. So get comfortable, but be prepared to lean in. What you are about to discover will shift your perspective on our place in the universe, sparking a sense of wonder you probably haven't felt since you were a kid staring up at the stars for the very first time. This is more than just a list. It's an exploration of the greatest story ever told, the story of everything, and it's a story that is still being written with every new discovery. Let's begin our adventure into the great unknown, starting with a fact that will change the way you think about our own solar system forever. Our journey into the cosmic unknown begins not in some distant galaxy, but right here in our celestial backyard with our closest companion, the Moon. It feels like a permanent fixture, an eternal sentinel in our sky, but that perception is an illusion of our brief human timescale. The truth is, the Moon is in a slow, steady retreat. Every single year, it moves approximately 3.8 centimeters farther away from Earth. That's about the same rate your fingernails grow. It might not sound like much, but over the immense spans of cosmic time, this tiny annual drift adds up to a dramatic rearrangement of the Earth-Moon system. This phenomenon is a direct result of the gravitational tug-of-war between Earth and the Moon, a dance powered by the ocean's tides. Here's how it works. The Moon's gravity pulls on our planet, and it pulls hardest on the world's most flexible feature, the global ocean. This creates a bulge of water on the side of Earth facing the Moon. However, because Earth rotates so much faster than the Moon orbits us, our planet's spin actually drags this tidal bulge slightly ahead of the Moon. This forward-positioned bulge of water, in turn, exerts its own slight gravitational pull on the Moon. This extra tug is minuscule, but it acts like a gentle, constant accelerator, giving the Moon a tiny bit of extra energy in its orbit. The laws of orbital mechanics are very clear. When an orbiting object gains energy, it must move into a higher, slower orbit. So, year after year, century after century, the Moon gets a gentle push and spirals outward. But this cosmic exchange has consequences for Earth too. The energy that pushes the Moon away has to come from somewhere, and it's being stolen from Earth's rotation. This means our planet's spin is very gradually slowing down, making our days longer. Billions of years ago, a day on Earth was only about 18 hours long. In the far, far future, days will be significantly longer than 24 hours. This also means that total solar eclipses, one of nature's most spectacular coincidences where the Moon perfectly covers the Sun, are living on borrowed time. The Moon's apparent size in our sky is shrinking as it moves away. Eventually, hundreds of millions of years from now, it will appear too small to completely blot out the sun, and total solar eclipses will vanish from Earth's experience forever. So, the next time you gaze up at the full moon, remember that you're looking at a companion that is slowly, inexorably saying goodbye. And speaking of cosmic disappearances, while our moon is slowly drifting away, another part of our galaxy is hiding a secret of an entirely different nature, one that might just make you think of a very unconventional happy hour. Floating near the center of the Milky Way, some 26,000 light-years away, is an immense dark cloud known as Sagittarius B2. This isn't just any cloud of gas and dust, it is a gigantic cosmic brewery. Within its vast expanse, which stretches over a region of space many times larger than our entire solar system, astronomers have detected the presence of billions and billions of liters of a simple organic molecule called vinyl alcohol. To be perfectly clear, this isn't the kind of alcohol you'd find in a cocktail. You wouldn't want to drink it, but its existence is absolutely staggering. This single interstellar cloud contains enough of this complex compound to fill our planet's oceans many times over. The question is, how does something as intricate as an alcohol molecule form in the cold, empty vacuum of space? The process begins inside these giant molecular clouds themselves. While we think of space as a perfect void, these clouds are relatively dense, though still far emptier than the best laboratory vacuum we can create on Earth. Within them, individual atoms like carbon, hydrogen, and oxygen drift aimlessly. Occasionally, they bump into each other, and if conditions are just right, they can stick together, forming simple molecules. But the real magic happens on the surface of tiny, floating dust grains. These microscopic particles act as cosmic catalysts, providing a solid surface where atoms can settle, meet their neighbors, and with a tiny boost of energy from starlight, link up into more complex chains. Over millions of years, these molecules build up, creating a rich, organic soup. The discovery of vinyl alcohol and many other complex organics like sugars and amino acid precursors in similar clouds fundamentally changes our understanding of the universe's chemical potential. It tells us that the basic ingredients for life, the very building blocks, aren't unique to Earth. The universe appears to be pre-processed, actively manufacturing these compounds long before planets even form. When a new star and planetary system eventually condenses from a cloud like Sagittarius B2, these complex molecules are already present, woven into the fabric of the nascent worlds. They could have been delivered to early Earth via comets and asteroids, potentially seeding our planet with the chemical prerequisites for life. So, that giant cloud of alcohol isn't just a fun astronomical curiosity, it's a profound clue. It suggests that the universe might be inherently biased towards creating the chemistry of life, that the ingredients for biology are a natural and widespread consequence of cosmic evolution. We are not separate from the universe. We are, in a very real chemical sense, a product of it, born from the same organic rich clouds that now drift between the stars. From our cosmic brewery drifting between the stars, we now travel inward to a world that defies all our Earth-based expectations about the flow of time itself. If you thought the moon's slow departure was a patient process, wait until you hear about the bizarre time warp happening on our nearest planetary neighbor, Venus. This is a place where the basic rhythms of day and night are completely turned on their head. On Venus, a single day, the time it takes for the planet to complete one full rotation on its axis, lasts an astonishing 243 Earth days. But the planet's journey around the Sun, its entire year, is completed in just 225 Earth days. Let that sink in for a moment. A year on Venus is shorter than a single Venusian day. If you were to stand on its scorching surface, you would celebrate your birthday before you ever saw the sun rise and set just once. This incredible fact stems from two deeply peculiar characteristics of Venus. First, its rotation is incredibly slow, the slowest of any major planet in our solar system. But second, and even more strangely, Venus rotates in the opposite direction of almost every other planet. This is known as a retrograde rotation. Look down on the solar system from above the Sun's north pole, and you'll see Earth, Mars, Jupiter, and Saturn all spinning counterclockwise. Venus, however, spins clockwise, so on Venus the Sun would appear to rise in the west and set in the east, a complete reversal of our experience. How did Venus end up like this? Scientists have several compelling theories, and the leading hypothesis involves a catastrophic event in the planet's distant past. The most widely accepted idea is that early in the solar system's history, when planets were still forming from a chaotic disk of debris, a colossal impact occurred. A massive object, perhaps a planetary embryo the size of Mars, could have slammed into Venus with such force that it literally knocked the planet upside down. This wouldn't mean the planet flipped over entirely, but rather that the impact altered its angular momentum, dramatically slowing its spin and potentially reversing its direction. Think of it like striking a spinning top with a hammer. The top would wobble violently and its spin would change drastically. Another theory suggests that Venus's incredibly thick, heavy atmosphere plays a role. The atmosphere of Venus is almost 100 times more massive than our own, a suffocating blanket of carbon dioxide with clouds of sulfuric acid. The gravitational tug-of-war between this super-dense atmosphere and the Sun's tidal forces, combined with friction between the atmosphere and the planet's surface, could have acted as a constant brake over billions of years, gradually slowing the planet's spin to its current crawl. It's possible that both a giant impact and atmospheric braking worked in tandem to create the world we see today. The consequences of this slow, backward spin are profound. A Venusian solar day, the time from one noon to the next, is actually quite different from its rotational day. Because the planet is moving in its orbit while it slowly rotates, it has to turn just a little bit more than a full 360 degrees for the Sun to return to the same point in the sky. This makes a true day on Venus from sunrise to sunrise last about 117 Earth days, so you would experience just under 2 full days for every single trip around the Sun. This strange chronology creates an environment unlike any other, where the Sun, if you could see it through the perpetual cloud cover, would creep slowly across the sky for months on end. It's a stark reminder that the familiar cycles we take for granted on Earth are not universal laws, but merely the specific conditions of our own very special world. But that strange and sluggish dance of Venus pales in comparison to the energetic mystery unfolding at the very edge of our solar system. Far beyond the rocky inner planets and the gas giant kingdoms of Jupiter and Saturn lies Neptune, a frigid, blue world so distant that the Sun appears as little more than an intensely bright star. At that incredible range, you would expect this planet to be a frozen, dormant ball, receiving only a tiny fraction of the solar energy that warms Earth. And you'd be right about the sunlight. Neptune gets just 1/900th of the energy we do. Yet when astronomers measure the heat radiating from Neptune, they find something astonishing. This icy giant is glowing with an intense internal fire, emitting about 2.6 times more energy than it ever receives from the Sun. It's a planet with its own powerful furnace, defiantly warm in the cosmic deep freeze. So, where does all this extra heat come from? The answer lies in the planet's dramatic birth and a slow-motion collapse that has been ongoing for billions of years. The leading explanation is a process called Kelvin-Helmholtz contraction, or gravitational compression. Imagine Neptune as a massive sphere that is still, ever so slightly, shrinking under its own immense weight. When the planet first formed, it accumulated an enormous atmosphere of hydrogen and helium from the primordial solar nebula. This creation process was violent and rapid, leaving the newborn world hot and puffed up. In the 4.5 billion years since, it has been slowly cooling and critically contracting. As gravity pulls the planet's material inward, that gravitational energy has to go somewhere. It gets converted into heat through friction and pressure, much like how a bicycle pump gets warm when you compress the air inside it. This residual heat from formation is then gradually leaking out from the planet's interior, providing that unexpected warmth. This internal engine has profound effects on Neptune's atmosphere, driving weather systems of unbelievable ferocity. While the sun is too weak to be the main driver of storms, the heat welling up from below creates tremendous temperature differences between the lower and upper atmosphere. This sets up violent convection currents like a pot of water boiling on a stove. These currents fuel the fastest winds in the solar system, which can rip across the planet at speeds exceeding 2,000 kilometers per hour. That's faster than the speed of sound on Earth. The Great Dark Spot observed by the Voyager 2 spacecraft was a colossal storm system, similar to Jupiter's Great Red Spot but even more powerful, believed to be directly powered by this churning internal heat. This makes Neptune a world of paradoxes, a planet that should be frozen solid based on its distance from the Sun, yet one that is dynamically alive with an energy all its own, a testament to the long-lasting power of its creation. But the idea of a world glowing with its own internal heat is just one example of the universe's capacity for creating extremes. For a true demonstration of cosmic alchemy, we must venture far beyond our solar system to a stellar graveyard where the death of a star has forged something almost beyond imagination, a planet made of diamond. This isn't science fiction, it's the reality of a world known as PSRJ 1719-1438b, a name that belies its incredible nature. This exotic planet orbits not a main sequence star like our Sun, but a pulsar, the rapidly spinning, incredibly dense corpse of a star that died in a supernova explosion. The story of this diamond planet begins with a violent stellar death and a cosmic partnership that went terribly wrong. Astronomers believe the system started with two stars orbiting each other. One was more massive than the other and lived out its life much faster, eventually exploding as a supernova. What remained was its incredibly dense core, a city-sized object with more mass than our Sun, spinning hundreds of times per second and blasting beams of radiation across the galaxy, a pulsar. The second star, a white dwarf, remained. A white dwarf is itself the exposed core of a star that wasn't quite massive enough to go supernova. It's what our Sun will become. It's incredibly dense, made mostly of carbon and oxygen, but it's still a star. In this binary system, the pulsar began to act as a cosmic vampire. Its immense gravity started pulling material away from the white dwarf companion. Over millions of years, the pulsar siphoned off almost all of the white dwarf's hydrogen and helium atmosphere, stripping it down to its bare core. What was left was a bizarre remnant, the core of the white dwarf, which had been robbed of so much mass that it could no longer be considered a star. It was now just an ultra-dense ball, primarily of crystallized carbon, orbiting the pulsar. This remnant is what we now call PSRJ 1719-1438b. The conditions that created this world are so extreme they boggle the mind. The gravitational pull from the pulsar is so powerful that it has compressed this carbon-rich ball to an astonishing density. Scientists estimate this diamond planet has a mass slightly greater than that of Jupiter, but it is compressed into an object only about 5 times the size of Earth. This creates unimaginable pressure within its core, pressure so intense that the carbon atoms are forced into a rigid, crystalline structure, a diamond. And we're not talking about a few gemstones scattered on the surface. The entire planet, or at least a significant portion of its interior, is likely one single gigantic crystal of diamond, potentially thousands of kilometers across. To put its value into a purely theoretical and utterly impractical perspective, the diamond that makes up this planet would be worth quintillions upon quintillions of dollars here on Earth, a number so large it's meaningless. But its true value is scientific, offering a glimpse into the most exotic outcomes of stellar evolution. This discovery fundamentally challenges our definition of a planet. This object wasn't born from a disk of dust and gas around a young star like the planets in our solar system. It is the gutted, crystallized corpse of a star that was cannibalized by its partner. It exists in a system of absolute extremes, bathed in intense radiation from its pulsar sun, a place where life as we know it would be instantly obliterated. The existence of such a world tells us that the universe is far more creative and bizarre than we ever conceived. It proves that under the right conditions of heat, pressure, and cosmic violence, matter can be transformed into the most fantastical forms. Out there in the darkness, a diamond the size of a world slowly orbits the ghost of a dead star, a permanent monument to the incredible forces that shape our cosmos. Now, if a world-sized diamond challenges our imagination, then our very own sun presents a mystery that has baffled physicists for decades, a puzzle that exists right on our cosmic doorstep. It's a fact that seems to defy basic logic. The sun's atmosphere is unimaginably hotter than its surface. Think about walking away from a campfire. The further you get, the cooler the air becomes. The sun operates on the opposite principle. Its visible surface, the photosphere, is a roiling sea of plasma at a temperature of around 5,500 degrees Celsius. That's hot enough to vaporize any material we know. But if you travel upward from that surface into the wispy, ethereal outer atmosphere called the corona, the temperature doesn't drop. It soars, skyrocketing to a staggering 1 to 2 million degrees Celsius. This is the coronal heating problem, and it's one of the longest-standing unsolved mysteries in solar science. How can the atmosphere be hundreds of times hotter than the surface below it? It's as if the air in your room was somehow scalding hot while the radiator itself was merely warm. For a long time, this was simply an observational curiosity. During a total solar eclipse, when the moon blocks the blinding light of the sun's main disk, the corona becomes visible as a beautiful, pearly white halo of delicate tendrils and streamers. Early spectrographs that analyzed the light from this corona revealed a telltale signature of highly ionized iron atoms, atoms that have been stripped of many of their electrons. For that to happen, the gas must be incredibly energetic, existing at temperatures in the millions of degrees. The immediate question is, what is the furnace? The energy source for the sun is nuclear fusion at its core, and that heat should gradually decrease as you move outward. So, something must be transferring a tremendous amount of energy directly into the corona, bypassing the surface entirely. The prime suspect has always been the sun's powerful and complex magnetic field. Unlike Earth's relatively simple bar magnet-style field, the sun's magnetic field is a tangled, dynamic mess. It's generated by the churning motion of plasma deep within the sun, and it erupts through the surface in massive loops and arcs. Two leading theories have emerged to explain how this magnetic chaos heats the corona. The first involves countless tiny explosions known as nanoflares. Imagine the massive solar flares we sometimes see, tremendous eruptions that release energy equivalent to billions of atomic bombs. A nanoflare is a much smaller version of this, but they are thought to be constantly popping off all across the sun, millions of them every second. Each nanoflare is caused by the sun's magnetic field lines becoming stressed, twisting and stretching until they snap like overwound rubber bands, releasing a burst of energy. Individually, a nanoflare is minuscule, but collectively, this endless barrage of tiny explosions could deposit enough energy to keep the corona consistently sizzling at millions of degrees. The second theory focuses on a more dramatic process called magnetic reconnection. This occurs when magnetic field lines pointing in opposite directions are forced together. They don't just bounce off each other, they can break and then rapidly reconnect into a new, lower energy configuration. This reconnection process is extraordinarily efficient at converting magnetic energy into heat and kinetic energy, violently accelerating particles to near the speed of light. It's like crossing two stretched rubber bands, cutting them, and then tying the loose ends together. The sudden release of tension sends them flying. On the Sun, magnetic reconnection is believed to be the engine behind large solar flares and coronal mass ejections, but it's also likely happening on smaller, more continuous scales throughout the corona, providing a steady heat source. The truth probably involves a combination of both mechanisms, along with other processes like powerful plasma waves traveling along magnetic field lines and dissipating their energy like ocean waves crashing on a shore. Solving this puzzle isn't just an academic exercise. The superheated corona is the source of the solar wind, a constant stream of charged particles that flows throughout the solar system. When this wind interacts with Earth's magnetic field, it creates the beautiful auroras, but intense solar storms driven by coronal activity can also disrupt satellites, knock out power grids, and pose a radiation risk to astronauts. Understanding how the corona is heated is fundamental to understanding our star's influence on our technological world, making this seemingly abstract mystery incredibly practical and urgent. If you think the paradox of the Sun's atmosphere is a strange puzzle, wait until you get a load of one of Saturn's most peculiar satellites, a moon that looks like a cosmic yin-yang symbol. Meet Iapetus, a world that presents astronomers with a mystery as stark as its own appearance. One hemisphere is as bright as freshly fallen snow, while the other is as dark as charcoal. This isn't a subtle gradient, it's one of the most dramatic color contrasts in the entire solar system. The leading theory to explain this two-tone facade is a captivating tale of celestial theft and a self-reinforcing feedback loop that turned half a world permanently dark. The story begins not with Iapetus itself, but with another, more distant moon of Saturn named Phoebe. Phoebe is a dark, irregularly shaped object that orbits Saturn in the opposite direction to most of its other moons, a characteristic known as a retrograde orbit. This backward journey is a crucial clue, suggesting that Phoebe might be a captured object, an ancient wanderer from the Kuiper belt that fell into Saturn's gravitational grasp long ago. As Phoebe travels its path, it is constantly bombarded by micrometeorites, which kick up a faint spray of dark, dusty material from its surface. Because Phoebe orbits backwards, this ejected dust tends to drift inward, slowly spiraling down toward Saturn. And right in its path, you guessed it, Iapetus. Imagine Iapetus as a giant, slow-moving windshield plowing through a cloud of dark soot. The moon's leading hemisphere, the side that always faces forward as it orbits Saturn, steadily collects this infalling Phoebe dust. But this initial coating of dark material was just the trigger for a much more powerful process. Here's where the real magic, known as thermal segregation, takes over. The newly deposited dark dust on Iapetus's leading face is less reflective than the underlying bright ice. A darker surface absorbs more sunlight, which causes it to warm up. Even in the frigid environment of the outer solar system, this slight warming is enough to have a dramatic effect. The ices on that darkened hemisphere, primarily water ice, begin to sublimate. That is, they turn directly from a solid into a gas, bypassing the liquid phase entirely. This sublimating ice then travels across the moon's surface and refreezes onto the colder, brighter areas, particularly the trailing hemisphere and the poles. This process creates a powerful positive feedback loop. As the leading hemisphere gets darker, it gets warmer, causing more ice to vaporize away, which makes it even darker and warmer. Meanwhile, the trailing hemisphere, now receiving a fresh coat of bright, reflective ice, becomes even brighter and colder, reinforcing the contrast. Over millions of years, this process carved Iapetus into the starkly divided world we see today. The evidence for this theory is compelling. Detailed observations from spacecraft like Cassini show that the dark material is indeed very thin, merely a blanket draped over the landscape, and its composition matches the dark, carbon-rich material we associate with objects like Phoebe. Furthermore, the boundary between the light and dark regions, named the Cassini Regio after the astronomer who first observed the moon's strange nature, is remarkably sharp and follows the exact line you would expect from this thermal process. It's a perfect example of a relatively small initial change, a sprinkle of dark dust being amplified by a world's local conditions into a global, defining characteristic. Iapetus stands as a giant natural experiment, demonstrating how subtle forces, given enough time, can create some of the most striking and beautiful anomalies in our cosmic neighborhood. From the stark duality of Iapetus, we turn our attention to a tempest of a completely different scale, a maelstrom so vast it could swallow our entire planet whole. For centuries, Jupiter's Great Red Spot has been the most iconic feature in our solar system, a swirling crimson eye staring out from the face of the gas giant. This is not just a storm, it is the storm, an anti-cyclonic monster of unimaginable power. Winds at its periphery scream at speeds exceeding 430 kilometers per hour, and its sheer size, though changing, has historically been so immense that 2 or 3 Earths could fit comfortably within its boundaries. We have records of this spot dating back to the 1830s, suggesting it has been churning for at least 190 years, and some evidence hints it could be far older. Yet, this seemingly permanent fixture of our cosmic map is undergoing a profound transformation. For the past several decades, astronomers have been watching with a mix of fascination and melancholy as the Great Red Spot is steadily, unmistakably shrinking. The change is both visible and measurable. When the Voyager spacecraft flew by Jupiter in 1979, the storm stretched over 23,000 kilometers in width, wide enough to hold 3 Earths side by side with room to spare. Recent observations from the Hubble Space Telescope and the Juno spacecraft now show its width has diminished to approximately 16,000 kilometers. That's still large enough to engulf our world, but the rate of shrinkage is significant, about 900 kilometers per year. Not only is it getting smaller, but its shape is also evolving, becoming less of a wide oval and more circular. This raises a compelling and urgent question. Is the Great Red Spot dying? The answer is complex, as the storm is not a simple weather system, but a dynamic feature deeply entwined with the chaotic energy of Jupiter's atmosphere. To understand its fate, we must first consider its origins and what fuels its longevity. Unlike hurricanes on Earth, which are powered by warm ocean water and quickly dissipate over land, the Great Red Spot has no solid ground to crash into. It is a self-sustaining atmospheric engine. It's essentially a gigantic wedge of high-pressure gas rotating anticlockwise, a high-pressure system that acts like a colossal atmospheric bearing. It's kept stable by its position between 2 of Jupiter's powerful, oppositely flowing jet streams. These zonal winds act like conveyor belts, shearing the edges of the storm and helping to maintain its spin. The storm also draws energy from the immense heat welling up from Jupiter's interior, a remnant of the planet's formation, much like the internal heat we discussed on Neptune. This combination of surrounding wind dynamics and internal planetary energy has allowed the spot to persist for centuries. So why is it shrinking now? Scientists propose several intertwined theories. One possibility is that the storm is interacting with smaller, temporary storms that are constantly popping up across Jupiter's turbulent face. These vortices, some white and some red, can get caught in the spot's gravitational pull and be absorbed, but the process might not always be smooth. A collision with a particularly large vortex could disrupt the spot's internal structure, essentially robbing it of some of its energy and momentum and causing it to contract. Another, more fundamental idea involves changes in the very jet streams that confine it. If these planetary winds are weakening or shifting their paths due to deeper atmospheric changes we cannot yet observe, the spot would lose the external support that has helped maintain its size for so long. It's like a spinning top that begins to wobble when the surface it's on starts to tilt. What does the future hold? Some models suggest the shrinkage could continue until the storm eventually fragments and dissipates entirely, perhaps within our lifetime. Other models indicate it might reach a stable, smaller size and persist for many more decades. There's even a historical precedent for disappearance. In the late 20th century, Jupiter's 3 smaller white oval storms, which had been observed for 60 years, suddenly merged into a single feature. The atmosphere of a gas giant is a system of immense complexity, and predicting the behavior of its largest storm is an enormous challenge. The ongoing Juno mission, with its regular close passes over Jupiter's poles, is providing unprecedented data on the planet's deep weather layers, which may finally unlock the secrets of the Great Red Spot's vitality. Whether it fades away or stabilizes, its transformation serves as a powerful reminder that even the most colossal and seemingly permanent features in our solar system are transient. We are living in a unique moment, able to witness the slow-motion evolution of a giant, a storm that has witnessed centuries of solar system history, and now, before our very eyes, is writing its final chapter. But if you think a shrinking storm on Jupiter is a sign of cosmic change, consider an even more profound form of wandering. For all our talk of solar systems with their orderly planets circling parent stars, we have been operating under a fundamental assumption that every planet has a sun. But this is not a universal rule. Drifting through the immense blackness between the stars are countless lone wolves, dark and frozen worlds that belong to no one. These are rogue planets, and their existence forces us to rethink what it means to be a planet at all. A rogue planet, also known as an interstellar planet or an orphan planet, is a planetary mass object that is not gravitationally bound to any star. It does not orbit a sun. It travels on a solitary path through the galaxy, forever cut off from the light and warmth of a solar hearth. The idea of such a world seems like science fiction, a desolate setting for a dark tale, but astronomers are now confident they are not just rare anomalies. They might be one of the most common types of planetary body in the entire Milky Way, potentially outnumbering stars by a ratio of 20-1 or even more. So how do these lonely worlds come to be? There are 2 primary pathways to planetary exile. The first and perhaps most dramatic method is ejection. In the chaotic early days of a young solar system, planets are forming from a disk of gas and dust, their orbits still unstable. As these fledgling worlds jostle for position, a gravitational tug-of-war ensues. In many systems, a close encounter between 2 or more large planets can be catastrophic. One of them, usually a Jupiter-sized giant, can act as a gravitational slingshot, flinging a smaller sibling out of the system entirely. This ejected planet is then set adrift, its velocity just enough to escape the star's gravitational pull forever. It's a cosmic game of pinball where the loser is banished to the eternal night of interstellar space. The second method is more solitary. Some rogue planets may never have had a star to begin with. Small, dense clouds of gas and dust scattered throughout galaxies can, under the right conditions, collapse under their own gravity. If such a cloud is too small to ignite the nuclear fusion that creates a star, it might instead form a planet directly. A failed star of sorts, but one that looks and behaves much like a gas giant. These objects, sometimes called sub-brown dwarfs, are born alone and wander from their very inception. Detecting these dark wanderers is one of astronomy's greatest challenges. Without a star to illuminate them, they are virtually invisible to traditional telescopes. The primary method for finding them relies on a cosmic quirk of gravity known as microlensing. When a rogue planet passes almost directly between a distant star and our telescopes here on Earth, its gravity acts as a tiny lens, bending and focusing the background star's light for a brief period. This causes the star to appear to brighten for a few hours or days before fading back to normal. By analyzing the characteristic signature of this brightening event, astronomers can deduce the mass and approximate distance of the invisible object that caused it. It's like finding a hidden object by seeing how it distorts the light behind it. Each microlensing event is a precious data point, slowly revealing the vast population of these invisible nomads. The environment on a rogue planet would be the definition of extreme. With no external source of heat, its surface would be plunged into temperatures only a few degrees above absolute zero, making even the icy moons of the outer solar system seem balmy in comparison. Any atmosphere would likely be frozen solid, falling as snow onto a barren landscape. Any potential for life as we know it would seem impossibly remote. However, there is a fascinating caveat. If a rogue planet were a gas giant with a large, icy moon, and if that moon had a subsurface ocean kept liquid by tidal heating from the planet's gravity, much like Jupiter's moon Europa, then it's conceivable, though wildly speculative, that life could persist in that isolated, sunless sea, powered by geothermal vents on the ocean floor. It's a long shot, but it hints that the seeds of life might be even more widespread and tenacious than we ever dreamed. The existence of these countless dark worlds profoundly changes our perspective. It suggests that our familiar, sun-centered model of a planetary system is just one possible configuration. There may be more planets drifting alone in the darkness than there are orbiting stars in the light. They are the ghosts of gravitational past, the failed formations, the exiled members of stellar families. Their silent journey through the galaxy reminds us that stability is a fragile thing and that the cosmos is filled with orphans, silently tracing their paths through the infinite void. While the Great Red Spot undergoes its slow transformation and rogue planets wander in perpetual night, another world in our solar system is literally tightening its belt, growing smaller right before our eyes. This brings us to our 10th astonishing fact: the planet Mercury is still shrinking. You might think of planets as largely static, unchanging spheres once they've formed, but Mercury is a dramatic exception. It is actively contracting, a process that has left its surface scarred with some of the most unique and telling geological features in our solar system, immense cliffs known as lobate scarps. To understand why Mercury is shrinking, we need to look deep inside the planet at its core. Mercury is an unusual world, possessing a disproportionately massive iron core that makes up about 60% of its total mass. For comparison, Earth's core accounts for only about 30% of its mass. This enormous metallic heart was incredibly hot when the planet first formed over 4.5 billion years ago. In the billions of years since, that core has been steadily cooling down. As metals cool, they contract, they take up less space. Now, imagine this happening on a planetary scale. The entire interior of the planet is slowly compressing, like a dried-out apple that wrinkles as it loses moisture. But unlike the flexible skin of an apple, Mercury's single, rocky outer shell, its crust and mantle, is brittle. It cannot simply fold inward uniformly. Instead, as the planet's interior shrinks, this outer shell has no choice but to crack and break, thrusting sections of itself upward and over other sections to accommodate the reduced volume. This is the genesis of the lobate scarps. These scarps are not like the gentle slopes of hills on Earth. They are colossal thrust faults, essentially giant cracks in the planet's crust where one block of rock has been pushed up and over another. They can be hundreds of kilometers long and soar up to 3 kilometers high, making them some of the most significant cliff faces in the solar system. Their name, lobate, comes from their distinctive curved or lobed appearance when viewed from above, reminiscent of a wave frozen in stone. The most famous of these, Discovery Roups, stretches for over 500 kilometers and has a steep slope that rises more than 1.5 kilometers above the surrounding terrain. If you were standing at its base, it would appear as an endless, towering wall of rock, a stark monument to the planet's ongoing transformation. What makes the discovery of these scarps so revolutionary is the evidence that this shrinking is not just ancient history. It is geologically recent and likely ongoing today. The key clue lies in the scarps themselves. As the Messenger spacecraft mapped Mercury's surface in exquisite detail, it found that many of these great cliffs have sliced through other, much younger geological features, such as small, young impact craters. When an asteroid or comet creates a fresh crater, it leaves a perfectly defined bowl-shaped depression. If a lobate scarp then forms and cuts directly across that crater, distorting its circular shape, it provides a clear sequence of events. The crater formed first and the scarp formed later. By analyzing the number and preservation state of craters that have been cross-cut by scarps, planetary geologists can estimate their age. The staggering conclusion is that some of this tectonic activity, this global contraction, has occurred within the last 300 million years, a mere blink of an eye in geological time. There is no reason to believe the process has stopped. Mercury's core is still cooling, meaning the planet is almost certainly still shrinking, millimeter by millimeter, century after century. This ongoing activity makes Mercury far more dynamic than its ancient, cratered face would otherwise suggest. It was long thought to be a geologically dead world, much like our moon, having exhausted its internal heat billions of years ago. The evidence for recent shrinkage forces a major revision of that view. Mercury retains enough internal warmth to drive global tectonic stresses, a finding that has implications for our understanding of other small, rocky worlds. It demonstrates that a planet's geological lifespan is not solely determined by its size, but by the specific composition and thermal history of its interior. The subtle, relentless contraction of this small world serves as a powerful reminder that even the seemingly quietest places in our solar system have their own slow, powerful rhythms of change, quietly reshaping their surfaces long after their violent birth. This striking permanence brings us to one of the most profound and poetic legacies of human exploration, the footprints left on the moon by the Apollo astronauts. Unlike on Earth, where a footprint on a beach is erased by the next tide or a gust of wind, those iconic impressions in the lunar soil are not temporary marks. They are, for all intents and purposes, permanent artifacts likely to endure for millions of years. The reason for this incredible longevity lies in the moon's profound lack of a dynamic environment. Our planet is a world of constant change, sculpted by an atmosphere that generates wind and weather, and by water that flows in rivers and oceans. These forces work tirelessly to erode and smooth the landscape, wiping away any trace of our passage in a relatively short time. The moon, by contrast, exists in a state of near-perfect stasis. It has no atmosphere to speak of, which means there is no wind to blow dust and gently fill in the footprints. There is no flowing water to wash them away. The primary forces of change on the lunar surface are not gentle and continuous, but immensely powerful and incredibly rare. The occasional impact of a micrometeorite and the gradual bombardment of solar and cosmic radiation. This creates an environment where even the most delicate impressions can be preserved with astonishing fidelity. The lunar soil, known as regolith, is a fine, abrasive dust created by eons of meteorite impacts pulverizing the bedrock. When an astronaut stepped into it, the particles compacted and sintered together, forming a cohesive impression. Without wind or water to disturb it, that shape is locked in place. It's a fossilization process that happens in an instant, capturing a single moment in time with the precision of a geological record. But the footprints are just the most visible human signature. The entire landing sites of the Apollo missions are now protected archaeological zones frozen in time. The descent stages of the lunar modules, the scientific instruments like the lunar laser ranging retroreflectors that we still use today to measure the Earth-Moon distance, the discarded geological tools, and even the famous lunar rovers, all of these artifacts sit exactly as they were left, silently gathering a thin layer of space dust at a rate of about 1 millimeter per million years. They are not rusting or decaying in the conventional sense, as there is no oxygen to facilitate corrosion. Instead, they are subjected to a much slower, more alien form of degradation, the relentless assault of atomic particles from the solar wind and cosmic rays, which can gradually darken and damage materials over immense timescales. This leads to a fascinating thought experiment about the ultimate fate of these sites. Over tens of millions of years, the slow, steady rain of micrometeorites will act like a gentle sandblaster, eventually eroding the equipment and potentially erasing the footprints. However, this process is so gradual that the sites will remain recognizable for a geological epoch. The footprints themselves, being shallow depressions, might be filled in by the seismic vibrations or moonquakes that occasionally ripple across the lunar surface, but even that is a slow and uncertain process. This permanence transforms the Moon into a unique museum of human achievement. It means that long after our civilizations have transformed beyond recognition on Earth, these quiet testaments to our first steps beyond our home planet will remain, a silent message to any future visitors, human or otherwise, that we were once here and we reached for the stars. It's a humbling reminder that in the grand, patient timeline of the cosmos, our most fleeting actions in one environment can become our most enduring monuments in another. And from the enduring footprints that mark our past, we turn to a discovery that points directly to our future, a revelation that has fundamentally rewritten our understanding of the most airless, seemingly barren worlds. The idea of finding water ice on the Moon, or even more shockingly, on the scorching doorstep of the Sun that is Mercury, sounds like a contradiction. For centuries, we believed these worlds were bone dry, their surfaces baked by unfiltered sunlight or, in the Moon's case, subjected to a vacuum that should instantly vaporize any volatile substance. Yet, hidden in plain sight, or more accurately, hidden in permanent shadow, are vast reservoirs of water ice, a resource that changes everything. The key to this cosmic paradox lies in a simple but crucial feature: axial tilt. Unlike Earth, which has a significant tilt that causes its poles to point toward and away from the Sun throughout the year, giving each pole 6 months of continuous sunlight followed by 6 months of darkness, both the Moon and Mercury have an almost negligible axial tilt. Their rotational axes are nearly perpendicular to their orbits around the Sun. This geometry creates a remarkable phenomenon at their poles. Inside certain deep craters, the rims cast shadows so deep and permanent that sunlight has not reached the crater floors for billions of years. These are the coldest places in the inner solar system, with temperatures plunging to a staggering -250 degrees Celsius, colder even than the surface of Pluto. In these profound freezers, any water molecules that happen to arrive, whether from comet impacts or solar wind interactions, found a permanent trap. They hit the super-cold surface and instantly froze, accumulating layer upon layer over eons, preserved like fossils in a cosmic icebox. The evidence for this is now overwhelming. For the Moon, it came from a bold experiment in 1999. NASA's Lunar Prospector spacecraft deliberately crashed itself into a shadowed crater at the Moon's south pole. As it plowed into the soil, scientists hoped it would kick up a plume of debris that could be analyzed from Earth. While the plume wasn't directly observed as hoped, prior data from the spacecraft's neutron spectrometer had already revealed the telltale signature of vast amounts of hydrogen, a key component of water, concentrated exactly in these permanently shadowed regions. Later missions like India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter used sophisticated instruments to definitively detect the chemical fingerprint of water ice itself. The estimates are staggering, suggesting billions of tons of water ice could be locked away at the lunar poles. The discovery on Mercury, however, was even more startling. This is a planet where daytime temperatures soar to 430 degrees Celsius, hot enough to melt lead. The notion of ice surviving there seemed impossible. Yet, in the early 1990s, astronomers using powerful terrestrial radio telescopes pointed them at Mercury's poles and detected something extraordinary. patches of radar-bright material, reflecting signals in a way consistent with water ice. The confirmation came later from NAS, a messenger orbiter, which not only mapped these reflective areas but also used neutron spectroscopy, just as on the Moon, to detect hydrogen. The ice on Mercury is thought to be even more abundant, layered thick and potentially covered by a thin blanket of dark, insulating dust that protects it from the minuscule amount of stray heat in its environment. So, where did this water come from? The leading theory is a delivery service provided by comets and water-rich asteroids. Throughout the solar system's history, these icy wanderers have bombarded every planet and moon. When they strike a world with an atmosphere, the water often boils away or is broken down by chemistry. But on an airless body like the Moon or Mercury, a comet impact vaporizes the ice, sending water molecules bouncing across the surface. Most of them, hitting sunlit areas, would quickly be broken apart by solar radiation or lost to space. But a fortunate few would follow a random path that takes them into the eternal darkness of a polar crater. Once inside that cold trap, they are stuck forever, slowly building up the ice deposits we see today. It's a slow-motion harvest that has been ongoing for billions of years. The importance of this discovery cannot be overstated. Water is the oil of space exploration. It's not just for drinking, it's a vital resource for life support and growing food. But more critically for exploration, it can be split into its component parts, hydrogen and oxygen, which are the primary ingredients for rocket fuel. Finding vast caches of water ice on the Moon and Mercury effectively creates cosmic gas stations. Instead of launching all the propellant needed for a return trip from Earth at an astronomical cost, future missions could land near these polar deposits, mine the ice, and process it into fuel on site. This concept, known as in situ resource utilization, completely transforms the economics of deep space exploration. It turns the Moon from a mere destination into a stepping stone, a hub from which we can launch missions deeper into the solar system with far greater efficiency. The water ice on these worlds is no longer just a scientific curiosity. It is the enabler of humanity's future as a spacefaring civilization, the key that unlocks the next great chapter of exploration. Just when you thought space was a realm of sterile beauty and silent vacuum, along comes a comet that challenges our very senses, proving the cosmos can be profoundly, pungently smelly. Our 13th fact takes us on a journey with one of the most ambitious robotic explorers ever launched, the European Space Agency's Rosetta mission. In 2014, after a decade-long journey across the solar system, Rosetta finally reached its target, the duck-shaped comet known as 67P, Churyumov-Gerasimenko. Its lander, Philae, made a historic, though bumpy, touchdown on the surface, but it was the Rosetta orbiter itself, circling the comet for nearly 2 years, that made a discovery that tickled the nose of science, metaphorically speaking. Its onboard instruments, designed to sniff the comet's faint atmosphere, or coma, detected a cocktail of molecules that would be downright offensive on Earth: the distinct aroma of rotten eggs from hydrogen sulfide, and the sharp, unmistakable sting of ammonia, which smells strongly of horse urine. Now, before you picture astronauts holding their noses, it's crucial to understand that a comet's smell isn't something you could experience directly. In the near-perfect vacuum of space, these molecules are so sparse that they wouldn't register to a human sense of smell. But to Rosetta's sensitive mass spectrometers, each molecule was a clear and powerful signal, a direct line to the comet's chemical identity. This bizarre bouquet wasn't just a cosmic curiosity, it was a time capsule. Comets like 67P are considered icy leftovers from the formation of the solar system 4.5 billion years ago. They have spent almost all of their existence in the deep freeze of the outer solar system, far from the heat and radiation of the sun that could alter their pristine chemistry. This means the molecules Rosetta detected are essentially unchanged since the dawn of our planetary system. They are the original ingredients, the primordial stock from which everything, including our own Earth, was built. The presence of hydrogen sulfide and ammonia is particularly significant because they are key carriers of two fundamental elements for life, sulfur and nitrogen. Alongside water, carbon dioxide, and a host of other organic compounds also found by Rosetta, these smelly molecules complete a picture of a cosmically rich chemical factory. When we analyze the composition of a comet, we are effectively reading the recipe book for planet formation. The discovery tells us that the building blocks of planets were not just simple ices and rocks, but a complex blend of volatile compounds. The fact that these specific, pungent molecules have survived for so long suggests they were trapped within the comet's ice, protected like fossils in amber, until the sun's warmth began to vaporize them as the comet approached the inner solar system, allowing Rosetta to take its historic sniff. This has profound implications for one of the greatest questions in science, the origin of water and the ingredients for life on Earth. The theory of panspermia, in its broadest sense, suggests that the basic materials for biology could have been delivered to our planet from space. Comets in particular are prime suspects for having brought a significant portion of Earth's water, but Rosetta's findings added a crucial twist. When scientists analyzed the type of water ice on Comet 67P, they found its isotopic signature, a kind of chemical fingerprint, was different from the water in Earth's oceans. This suggests that while comets likely contributed, they may not have been the sole source of our water. However, when it comes to the other ingredients, the story is different. The smelly cocktail of ammonia and hydrogen sulfide, along with other complex organics, points to comets as being perfect delivery vehicles for the volatile elements and probiotic chemistry necessary for life to emerge. It's as if they weren't just delivering water, but also sprinkling the planetary soup with the essential salts and flavors. So, while the idea of a comet smelling like a barnyard might seem humorous or even repulsive, it's actually a sign of something magnificent. It's the scent of creation itself, the raw, unprocessed aroma of the nebula that gave birth to our sun and planets, a fragrance that, billions of years later, would eventually lead to the rich and living world we call home. Leaving behind the scented trails of comets, we arrive at a geological titan so immense it redefines the very concept of a mountain. On the rusty plains of Mars stands Olympus Mons, the largest volcano in the solar system, a feature so colossal that its dimensions are almost impossible to grasp. This is not merely a mountain, it is a planetary landmark of staggering proportions. To put it in perspective, Olympus Mons rises nearly 22 kilometers above the Martian surface. That is almost 2.5 times the height of Mount Everest above sea level, but its true awe lies in its footprint. The base of this volcano sprawls across an area roughly the size of the state of Arizona or the entire country of Italy. If you were standing on its outer slope, the summit would be hidden beyond the curvature of the planet itself. The peak would be below your horizon. So how did Mars, a planet half the size of Earth, produce a volcanic giant that so completely dwarfs anything on our own world? The answer lies in a fundamental geological difference. Mars is a one-plate planet. Here on Earth, our planet's crust is broken into a jigsaw puzzle of tectonic plates that slowly drift, collide, and slide past one another. This constant motion is crucial for volcanism. As a plate moves over a fixed hotspot of magma rising from the mantle, it creates a chain of volcanoes like the Hawaiian Islands. Each volcano in the chain is born, actively erupts for a few million years, and then is carried away from the heat source, becoming extinct. This process limits the size any single volcano can achieve. On Mars, however, this system does not exist. For reasons not fully understood, Mars lost its internal heat much faster than Earth, causing its tectonic activity to grind to a halt billions of years ago. The Martian crust effectively became a single, stationary plate. This meant that when a massive plume of hot magma rose from the planet's mantle, It stayed fixed in one place, erupting through the same spot in the crust for not just millions, but for hundreds of millions, even over 1 billion years. Instead of creating a chain of islands, all of that lava, ash, and rock piled up in one single gargantuan location, layer upon layer, eruption after eruption, building Olympus Mons to its unbelievable dimensions. The volcano's specific shape, a shield volcano with incredibly gentle slopes, is a direct result of this long-lived eruption style and the planet's lower gravity. The lava that built Olympus Mons was very fluid basaltic lava, similar to the kind that forms the Hawaiian Islands. It flowed easily and for great distances before cooling and solidifying. Because Martian gravity is only about 38% of Earth's, this lava could travel even farther and spread out more widely, creating those characteristic shallow slopes that make the volcano look less like a steep peak and more like a vast, gently sloping ramp. This low profile is deceptive. The climb to the summit would be a marathon of distance, not a sheer cliff face ascent. The caldera, the complex of collapsed craters at the very top, is itself about 80 kilometers wide, large enough to swallow entire cities. This caldera formed as the underlying magma chambers emptied during eruptions and the ground above them collapsed, a cycle that repeated multiple times over the volcano's immensely long life. The sheer longevity of Olympus Mons forces us to contemplate the vastly different timescales of planetary geology. This volcano wasn't built in a few cataclysmic events, but through a patient, persistent drip feed of lava that spanned eons. It was likely active for a significant portion of Martian history, a testament to a time when Mars was a much more geologically vibrant world with a hotter interior and a thicker atmosphere. Today, it stands as a silent, frozen monument to that bygone era. Evidence suggests its last eruption might have been as recent as 25 million years ago, which is practically yesterday in geological terms, hinting that the Martian interior may not be entirely dead yet. The existence of Olympus Mons doesn't just demonstrate the power of volcanism. It highlights how a simple change in a planet's internal engine, the presence or absence of plate tectonics, can lead to wildly different, almost unimaginable outcomes, creating landscapes on a scale that simply cannot exist on our own dynamic but divided world. From the monumental heights of Olympus Mons, we now travel to the outer solar system to encounter a world whose very orientation defies all convention. While most planets in our solar system spin like tops, with their rotational axes more or less perpendicular to their orbits, Uranus has decided to do a complete barrel roll. This ice giant is tilted at a jaw-dropping 98-degree angle, meaning it essentially orbits the Sun on its side. Imagine a globe where the North Pole is not at the top, but is pointing directly toward the path you're walking. For Uranus, this means its poles, not its equator, take turns facing the Sun during its 84-year-long orbit. For 21 Earth years, one pole experiences continuous sunlight, while the other is plunged into profound darkness. Then, as it continues its journey, the roles reverse. This extreme tilt gives Uranus the most unusual seasons in the entire solar system. The question of how Uranus ended up in this bizarre position is one of the great puzzles of planetary science, and the most compelling explanation points to a truly catastrophic birth. The leading theory suggests that in the violent early days of the solar system, when planetary orbits were still unstable and giant protoplanets jostled for position, a cataclysmic collision occurred. A young Uranus, still forming from the primordial disk of gas and dust, was struck by an object estimated to be at least twice the mass of Earth. This wasn't a glancing blow. It was a direct, shattering impact that likely occurred when the planet was still surrounded by its own disk of material, the building blocks for its future moons and rings. The consequences of such an impact would have been world-altering, literally. The force of the collision would have been enough to knock the entire planet sideways, reorienting its spin axis by nearly a right angle. Think of it like striking a billiard ball off-center with a tremendous amount of force. It wouldn't just move, it would start spinning on a completely new axis. The energy delivered would have been so immense that it could have also vaporized a significant portion of the planet's interior, potentially explaining one of Uranus's other enduring mysteries, its surprisingly low internal heat. Unlike Jupiter, Saturn, and Neptune, which all radiate more heat than they receive from the Sun, Uranus's internal temperature is almost exactly in equilibrium with the solar energy it absorbs. The giant impact theory offers a neat solution. The collision may have been so violent that it blasted away much of the planet's original internal heat, leaving it as the solar system's cold, quiet giant. An alternative, though less favored, theory proposes that Uranus's tilt was not the result of a single cataclysm, but a gradual process driven by gravitational tugs. In this scenario, a massive moon orbiting Uranus in the distant past could have exerted a persistent gravitational pull on the planet's equatorial bulge. Over hundreds of millions of years, this interaction, combined with gravitational resonances with the other giant planets, could have slowly torqued the planet onto its side. While plausible, many scientists find the singular impact theory more convincing, as it elegantly explains both the extreme tilt and the planet's anomalous lack of internal heat in one dramatic event. This unique orientation has profound effects on the planet's weather and magnetic field. Because the poles receive such extreme and prolonged heating, the atmospheric dynamics of Uranus are unlike those of any other planet. When the Voyager 2 spacecraft flew by in 1986, the pole facing the Sun appeared surprisingly bland, but more recent observations with the Hubble Space Telescope have revealed massive, powerful storms erupting as the planet approaches its equinox, the brief period when the Sun shines directly on its equator. Furthermore, Uranus's magnetic field is just as peculiar as its rotation. The field is not aligned with the planet's rotational axis, nor is it centered on the core. Instead, it is tilted by about 60 degrees and offset from the planet's center. This lopsided, tumbling magnetic field creates a magnetosphere that is wildly asymmetric, behaving more like a complex, chaotic web than the structured bubble that surrounds Earth. The story of Uranus is a stark reminder that the serene order often depicted in solar system models is a simplification. The reality is a history of cosmic violence and chance events, where a single accident billions of years ago can set a world on a path of eternal sideways rolling, creating a unique and enigmatic giant at the edge of our Sun's influence. While Uranus is a testament to a past cosmic collision, there is growing evidence that our solar system may be hiding another giant world, a ghost planet whose presence we can only infer from the ghostly traces it leaves on the far smaller objects in the deep freeze beyond Neptune. This brings us to one of the most tantalizing modern mysteries in astronomy, the hypothetical planet 9. This is not the reclassified Pluto we're talking about, but a potential true giant, a world with a mass perhaps 5 to 10 times that of Earth, orbiting so far away that it has eluded every telescope to date. The case for its existence is built not on a direct photograph, but on a pattern of gravitational whispers etched into the strange paths of icy bodies in the distant Kuiper belt. The Kuiper belt is a vast donut-shaped region beyond Neptune, filled with frozen remnants from the solar system's formation, of which Pluto is the most famous member. For years, astronomers have been tracking a specific group of these objects, known as extreme trans-Neptunian objects, or ETNOS. What makes them extreme is not just their distance, but the peculiar shapes of their orbits. These orbits are highly elongated, taking them incredibly far from the Sun, but they also share a curious and unexpected clustering. Imagine a handful of scattered leaves on a vast pond. If the wind is blowing, you'd expect them to drift in random directions. But if you observe that all the leaves are consistently drifting toward one specific corner of the pond, you might start to suspect there's an unseen current, a hidden drain pulling them that way. That's precisely what astronomers Konstantin Batygin and Mike Brown at Caltech observed in 2016. The orbits of these distant ETNOS weren't randomly oriented. Their points of closest approach to the Sun, their perihelia, were grouped together in space, and their orbits were tilted in a similar way. The statistical probability of this happening by pure chance is astronomically low, calculated to be around 0.0007%. The most elegant explanation for this orbital clustering is the gravitational influence of a massive, unseen planet. According to the models, a planet 9 with the proposed mass, following a stable but highly elliptical orbit that takes it hundreds of times farther from the Sun than Earth, would act as a cosmic shepherd. Over millions of years, its gravity would sculpt the orbits of these smaller objects, herding them into the specific, clustered configuration we observe today. It's a gravitational signature, a fingerprint left by a giant hiding in the dark. The predicted orbit for Planet 9 is immense, with a single trip around the Sun possibly taking between 10,000 and 20,000 years. At its closest approach, it might still be several times farther out than Neptune, and at its most distant, it would venture into the inner Oort cloud, a realm of profound isolation. The search for this elusive world is now one of astronomy's great treasure hunts, combining cutting-edge technology with painstaking, old-fashioned dedication. The challenge is immense. At such fantastic distances, even a large planet would reflect only a tiny, vanishingly faint trickle of sunlight. It's like trying to spot a single, dimly lit charcoal briquette lost in the expanse of a dark sports stadium. To make matters more difficult, astronomers don't know exactly where in its multi-thousand-year orbit it might be. They have a vast swath of sky to search, a celestial haystack with a needle that moves incredibly slowly. The primary tools in this search are the world's most powerful wide-field survey telescopes, like the Subaru telescope on Mauna Kea in Hawaii and the Dark Energy Survey camera in Chile. These instruments systematically photograph huge portions of the night sky over and over again. Powerful computers then compare these images, looking for any faint point of light that has moved just a tiny amount against the background of fixed stars. It is a monumental task of data analysis, sifting through petabytes of information for that one telltale pixel. What would Planet 9 be like if we found it? Its predicted mass places it in a category between Earth and the ice giants Uranus and Neptune, making it a super-Earth or a mini-Neptune, a type of planet that is common around other stars but mysteriously absent from our own inner solar system. Its composition would likely be similar to Uranus and Neptune, a rocky core surrounded by a thick mantle of water, ammonia, and methane ices, and enveloped in a deep atmosphere of hydrogen and helium. Its distance from the Sun would make it an eternally frozen world, with surface temperatures hovering near a bone-chilling -220 degrees Celsius. The discovery of Planet 9 would be a monumental achievement, not just for adding a new planet to our charts, but for fundamentally rewriting the history of our solar system. Its existence would imply a dramatic past, possibly involving a gravitational kick from Jupiter that sent it spinning out to the hinterlands early in the solar system's formation. It would solve the mystery of the clustered Kuiper belt orbits and potentially explain other anomalies, like the unusual tilt of the Sun's axis. For now, Planet 9 remains a hypothesis, a compelling ghost in the celestial machine. But the hunt continues, driven by the powerful conviction that the gravitational clues point to a hidden giant, waiting silently in the dark to be found. But if the silent dance of a hidden planet is a mystery we must unravel through mathematics and light, our next fact challenges one of our most fundamental sensory assumptions about the cosmos, the idea that space is a realm of perfect, eternal silence. It's true that in the void between stars and planets there is no air, no medium for the pressure waves that our ears interpret as sound to travel through. If you were to float in the emptiness near a supernova explosion, the cataclysm would be utterly, profoundly silent. Yet, to say space is completely silent is a dramatic oversimplification. The universe is filled with a hidden symphony of vibrations, and with the help of our robotic explorers, we can now translate these cosmic signals into sounds we can hear, revealing a universe that is far from mute. The key to unlocking this symphony lies in understanding the difference between sound and vibration. While the vacuum of space cannot carry sound waves, it is absolutely teeming with electromagnetic energy and swirling clouds of charged particles known as plasma. This plasma, though incredibly thin, can carry vibrations in the form of plasma waves. These are rhythmic oscillations in the electric and magnetic fields that permeate space, and they operate on principles similar to sound waves, having frequencies and amplitudes that we can measure. Our spacecraft are equipped with instruments specifically designed to detect these vibrations. They don't have microphones in the traditional sense. Instead, they use antennas and sensors to capture the fluctuating electric and magnetic fields. Scientists then take this data, these patterns of vibration, and transcribe them, shifting their frequencies down into the range of human hearing. This process, called sonification, allows us to experience the sounds of planets, stars, and magnetic fields for the very first time. The results are both haunting and beautiful, offering an entirely new way to perceive our solar system. One of the most famous examples comes from the Galileo spacecraft as it flew past Jupiter's largest moon, Ganymede. As it entered the moon's miniature magnetic field, its sensors picked up a dramatic change in plasma waves. When sonified, the data reveals a sudden, sharp crescendo of crackling static, a sonic snapshot of the moment the spacecraft crossed a fundamental boundary in space, a frontier invisible to the eye but roaring with energetic activity. It's the sound of plunging into a new magnetic environment, a crackle that conveys the dynamic interaction between a moon and its giant planetary host. Perhaps even more iconic are the eerie, choir-like sounds of Earth's own magnetic field. Our planet is surrounded by a protective bubble called the magnetosphere, which shields us from the constant stream of charged particles flowing from the sun, the solar wind. When this wind interacts with the magnetosphere, it doesn't hit a silent barrier. Instead, it generates a phenomenon known as chorus waves. When recorded by satellites like NASA Van Allen probes and converted to audio, these waves produce an uncanny sound reminiscent of birds chirping or dolphins whistling at the break of dawn. These aren't random noises, they are the direct result of electrons being accelerated along Earth's magnetic field lines, creating a natural electromagnetic dawn chorus that has been singing around our planet for billions of years. It's a constant, ethereal song of protection, a sound we walk around completely unaware of, yet one that is fundamental to the existence of life on our world. Venturing farther out, the Cassini spacecraft provided us with a stunning auditory experience of Saturn. The planet's immense magnetic field interacts with its rings in a complex dance, and Cassini's radio and plasma wave science instrument captured these interactions. The data, when sonified, produces a symphony of hisses, cracks, and pops that vary in intensity and pitch depending on which ring the spacecraft was near. It's as if each ring has its own distinct vibrational signature. Furthermore, the powerful radio emissions generated by Saturn's auroras, thousands of times stronger than Earth's, create a haunting, pulsing soundtrack, a deep space hum that speaks to the tremendous energies at play around the ringed giant. Even the Sun has a voice. The Solar and Heliospheric Observatory, or SOHO, has recorded the oscillations and vibrations rippling through the Sun's super-hot atmosphere. These are the waves that travel through the solar plasma, and when sped up into the range of human hearing, they produce a low, resonant, meditative hum, like the deepest note from a cosmic cello. This is the sound of a star breathing, a direct recording of the processes that churn within our star. By listening to these sounds, heliosseismologists can actually probe the Sun's interior structure, much like geologists use seismic waves from earthquakes to understand Earth's inner layers. The music of the sun is not just a curiosity, it's a vital diagnostic tool. This ability to hear the universe completely changes our relationship with it. It transforms abstract data into an experience that feels more immediate and visceral. The crackle of a planetary bow shock, the whistle of Earth's chorus, the hum of the sun, these sounds make the forces of nature tangible. They remind us that while the cosmos may not communicate through sound in the way we are used to, it is still a vibrantly dynamic and musical place, filled with rhythms and frequencies that tell the story of gravity, magnetism, and plasma physics. It is a hidden layer of reality, a symphony written in particles and fields, waiting for us to learn how to listen. But this hidden symphony of our local solar system is just a prelude to a far grander, more violent performance that is already scheduled in the cosmic calendar, a performance that will redefine our entire galaxy. We often think of the universe as a static, unchanging backdrop, but the reality is one of constant, dynamic motion on the most colossal scales. And the most significant event in the future history of our Milky Way is an unavoidable collision. The Andromeda Galaxy, our largest galactic neighbor, is not merely drifting in the void, it is hurtling directly towards us. In about 4.5 billion years, the Milky Way and Andromeda will meet in a gravitational embrace that will fundamentally reshape both galaxies forever. This isn't a prediction based on vague speculation. It's a conclusion drawn from painstakingly precise measurements. For decades, astronomers have been able to track the movement of the Andromeda Galaxy across the sky. While most galaxies are flying away from us due to the expansion of the universe, Andromeda is a striking exception. Because it is so close, at a mere 2.5 million light-years away, the gravitational attraction between our two massive galaxies overwhelms the expansion of space on this local scale. Using the Hubble Space Telescope, scientists have measured Andromeda's sideways motion and its velocity toward us with incredible accuracy, confirming that a direct collision is not just possible but inevitable. The timeline of 4.5 billion years might seem impossibly distant, but it gives us a profound perspective. Our sun will still be shining then, though it will have grown brighter and hotter, and Earth will be a very different world. This galactic merger is a future chapter in a story that is already unfolding. So, what will this cosmic crash actually look like for any hypothetical future observers? It's crucial to dispel a common misconception. This will not be a violent, destructive event like two cars smashing together. The distances between stars are so astronomically vast that a direct stellar collision is incredibly unlikely. Instead, the merger will be a slow, majestic dance lasting billions of years, governed entirely by gravity. The first close approach will be a sideswipe as the two galaxies pass through each other. During this pass, the gravitational tides will be immense. Long streams of stars and gas will be ripped from both galaxies, stretching out into spectacular tidal tails that will paint luminous arcs across the night sky. The familiar structure of the Milky Way as a neat spiral disk will be utterly distorted, its arms stretched and warped beyond recognition. As the galaxies swing past each other, they will slow, pulled back by their mutual gravity, and fall together for a second, more direct collision. This is when the real merger begins. Over the course of hundreds of millions of years, they will swing back and forth, each pass transferring energy and causing them to lose momentum, eventually settling into a single, tangled, ellipsoidal blob of stars. The result of this titanic union will be a new type of galaxy, an elliptical galaxy. This new entity, which some astronomers have already nicknamed Milkomda or Milkdromda, will be larger, featureless, and devoid of the beautiful spiral arms we associate with its progenitors. The process will also trigger a final, glorious burst of creation. The immense clouds of gas and dust within both galaxies will be violently compressed during the collisions, sparking a firestorm of new star formation, a stellar baby boom that will light up the merging galaxy with the brilliant blue light of millions of newborn stars. For any planetary systems caught in this upheaval, the direct risk is low, but the change in the night sky would be utterly transformative. Our solar system will likely be flung into a much wider orbit within the new elliptical galaxy. From our perspective, the familiar band of the Milky Way would vanish, replaced by a sky ablaze with a diffuse, incredibly bright glow from the combined light of hundreds of billions of stars. The tidy constellations we know would be completely scrambled, replaced by a brilliant, chaotic splatter of stars. While the Earth itself may be uninhabitable by then due to the Sun's evolution, the fact that our cosmic address is temporary adds a humbling, beautiful layer to our understanding of the universe. It teaches us that galaxies are not immortal islands, but dynamic entities that grow, evolve, and merge over time. Our own Milky Way is a product of past, smaller mergers, and the collision with Andromeda is simply the next step in its life cycle, a reminder that even the largest structures in the cosmos are part of an endless, graceful, and sometimes turbulent dance. From the cosmic symphony of galactic collisions, we now zoom into one of the most extreme and mind-bending objects the universe can produce, a place where the very nature of matter is pushed to its absolute limit. Imagine compressing an entire mountain with all its immense mass of rock and earth down into something that could fit in the palm of your hand. Now go far, far beyond that. We are talking about neutron stars, the dense skeletons of dead suns, and they possess a property so extreme it defies all earthly intuition. A single teaspoon of neutron star material would weigh billions of tons here on Earth. This isn't science fiction, it's the direct consequence of physics operating under conditions of almost unimaginable pressure. To understand how this is possible, we have to revisit the dramatic death of a star. Not all stars go out quietly. A star significantly more massive than our Sun ends its life in a cataclysmic supernova explosion, blasting its outer layers into space in a brilliant flash that can outshine an entire galaxy. What remains behind is the star's collapsed core. If this core is between about 1.4 and 3 times the mass of our Sun, it doesn't form a black hole, but instead becomes a neutron star. The force of gravity during this collapse is so stupendous that it overwhelms every other force in nature. It crushes the core down from a sphere roughly the size of a city to a ball only about 20 kilometers across, the size of a modest metropolis. In this incredible compression, the very atoms that made up the star are utterly demolished. Under normal conditions, an atom is mostly empty space. Think of a miniature solar system with a dense nucleus of protons and neutrons at the center, and tiny electrons whizzing around it in a vast orbital cloud. The distance between the nucleus and the electrons is enormous compared to their size. But inside a neutron star, gravity's crush is so powerful that it eliminates this empty space entirely. The incredible pressure forces the electrons to combine with protons, neutralizing their charge and transforming them into neutrons. The entire star becomes a seething ocean of neutrons packed together tighter than atoms in a solid. This is what physicists call neutron degenerate matter. It's a state of matter that cannot be created in any laboratory on Earth, a super-dense fluid where the subatomic particles are literally touching one another with no room left to compress further. It is the ultimate density possible for a material object before it crosses the threshold into becoming a black hole. This density is where the teaspoon analogy comes from, and the numbers are truly staggering. A typical neutron star has a mass about 1.4 times that of our Sun, but that mass is squeezed into such a tiny volume that its density is approximately 1 billion tons per cubic centimeter. To put that into a more relatable scale, if you could somehow scoop up a single teaspoon about 5 cubic centimeters of this material, it would have a mass of around 5 billion tons. That is equivalent to the mass of every single human being on Earth today, multiplied by over 600. Or, to use another comparison, it's about the same mass as a solid cube of Mount Everest, one of the most massive objects on our planet. The gravitational pull on the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you were to drop a marshmallow from a height of 1 meter above a neutron star, it would hit the surface with the energy of 1,000 hydrogen bombs, its atoms instantly fused into the degenerate matter of the star. The existence of neutron stars is a breathtaking demonstration of the power of fundamental forces. They are cosmic laboratories that allow us to test the laws of physics under conditions we can never replicate. Studying them through their pulses of radiation as pulsars, or by observing the gravitational waves they create when they collide, helps us understand the behavior of matter at nuclear density and the very fabric of space-time itself. These stellar remnants are not just inert cinders, they are the ultimate consequence of a star's battle with gravity, a battle that gravity wins by creating a substance of pure, unimaginable density, a single speck of which would possess more weight than all of humanity combined. Now, after contemplating the crushing density of neutron stars, we come to a celestial object that represents the opposite extreme of stellar evolution, a cosmic paradox that blurs the line between planet and star. Imagine a star not as a blazing inferno, but as a lukewarm ember, an object with a surface so surprisingly mild that you could, in theory, reach out and touch it without being incinerated. This is not a fantasy, it is the reality of a class of objects known as brown dwarfs, the failed stars of our galaxy. A brown dwarf is essentially a stellar underachiever. It forms in the same way a star does, from the collapse of a cloud of gas and dust under its own gravity, but the crucial difference lies in its mass. For a true star to be born, the collapsing cloud must accumulate enough mass to create immense pressure and temperature at its core, igniting the sustained nuclear fusion of hydrogen into helium. This process, which powers every star like our Sun, requires a minimum mass of about 75 to 80 times the mass of Jupiter. Brown dwarfs fall short of this threshold. They occupy a mysterious no-man's land between the most massive planets and the smallest stars, with masses ranging from about 13 to 75 Jupiters. They have enough mass to briefly ignite the fusion of a rare isotope of hydrogen called deuterium, and the very largest might even fuse lithium for a short time, but these are fleeting nuclear reactions. Without the sustained furnace of hydrogen fusion, a brown dwarf cannot generate its own significant, long-lasting source of heat. Instead, it simply glows with the residual warmth left over from its violent birth, and then slowly and inexorably cools down over billions of years, fading from a dim red to a dull infrared glow and eventually into invisibility. This cooling process is what leads to their most astonishing property. While a young, freshly formed brown dwarf can have a surface temperature of a few thousand degrees, an old, settled brown dwarf can cool to temperatures that are almost mundane. The record holders, known as white dwarfs, are the coldest known stellar objects. The most famous example, a brown dwarf named WISE 0855-0714, is located just 7.2 light-years away, and its surface temperature is estimated to be between -48 and -13 degrees Celsius. That is colder than a winter day in Siberia and squarely within the temperature range we experience on Earth. While you wouldn't want to actually touch it due to the lack of a breathable atmosphere and its immense gravity, the point remains: the thermal energy radiating from its surface is not inherently deadly. It's a star-like object with a temperature comparable to a freezer. Their composition is as strange as their temperature. Being too small to be stars but too large to be typical planets, brown dwarfs are thought to have atmospheres that are wildly exotic. As they cool, their atmospheric chemistry changes dramatically. In warmer brown dwarfs, astronomers have detected clouds of molten iron and silicate vapors, raining droplets of liquid metal. In the cooler white dwarfs, the conditions might be right for clouds of water vapor or even ammonia, creating weather patterns that are both familiar and utterly alien. Their interiors are a puzzle as well. The immense pressure likely squeezes their material into strange states, perhaps even forming a degenerate core of electrons, similar to the interior of a white dwarf star, but wrapped in a gaseous atmosphere. This makes them unique laboratories for studying atmospheric physics under conditions that don't exist anywhere else. Despite their name, brown dwarfs are not actually brown. They appear deep magenta or dull red to the human eye when they are young, fading to a dim infrared glow as they age. Their true significance lies in their ubiquity. For every true hydrogen-fusing star in our galaxy, there may be as many as 100 of these failed stars lurking in the dark. They are the invisible majority of the stellar population, too dim to see with optical telescopes but revealed by powerful infrared observatories like the WISE and Spitzer space telescopes. Their existence challenges our simple classifications and reveals a continuous spectrum of objects from gas giant planets to small red dwarf stars. The discovery of a touch temperature star reminds us that the universe is filled with quiet, subtle objects, not just the brilliant giants. They are the cosmic introverts glowing with a faint residual warmth, enduring on timescales that make even the longest-lived true stars seem fleeting. While the cold, quiet brown dwarfs represent one end of the cosmic spectrum, our own solar system is home to a storm of such perfect geometry it seems almost artificial. At Saturn's North Pole, a structure so bizarre and precise exists that when the Cassini spacecraft first beamed back images of it, scientists could scarcely believe their eyes. There, swirling atop the gas giant, is a colossal hexagon. This is not a trick of pixelation or a transient cloud formation. It is a persistent six-sided jet stream, a hurricane-like storm 20,000 miles across, with each side longer than the diameter of Earth. What makes this feature so astounding is its geometric perfection. In nature, we expect to see curves, spirals, and chaotic patterns, not a near-perfect hexagon etched into the atmosphere of a planet. It's as if a cosmic giant took a protractor and drew a boundary around Saturn's pole. The key to understanding this phenomenon lies not in solid structures, but in the complex physics of fluid dynamics. The hexagon is essentially a standing wave pattern, a stable ripple in Saturn's fast-moving atmosphere. Imagine a pot of water on a stove. As you stir it, you can create various patterns and vortices. Now imagine doing this on a planetary scale, with an atmosphere made mostly of hydrogen and helium, and you begin to grasp the forces at play. Scientists believe the hexagon is created by differences in the speed of Saturn's internal winds at various latitudes. Deep within the planet, the roiling interior generates massive jet streams that flow eastward. At a certain latitude, there is a particularly sharp gradient in the wind speed, a sudden jump in velocity. When a fluid, even a gaseous one like an atmosphere, moves past such a boundary, it can become unstable and generate waves. In laboratory experiments, when a circular tank of fluid is rotated at different speeds at its center and edges, similar polygonal shapes, including hexagons, can emerge. The specific six-sided shape on Saturn likely arises from the particular speed and depth of the jet stream at that latitude, creating a resonant wave that locks into a stable geometric pattern. What's truly remarkable is the hexagon's longevity. It was first observed by the Voyager spacecraft in the 1980s, and when Cassini arrived over 2 decades later, it was still there, unchanged. This stability is a testament to the sheer scale and power of Saturn's weather systems. On Earth, even the largest storms are fleeting, lasting weeks or months at most, because they are disrupted by landmasses, oceans, and a relatively thin atmosphere. Saturn, however, is a uniform ball of gas with no solid surface to create friction. Its atmosphere is incredibly deep, and the forces that generate the hexagon are so immense and consistent that the pattern can persist for decades and likely much longer. Inside the hexagon, the weather is just as dramatic. the central region is dominated by a massive, swirling hurricane with an eye so vast it could swallow entire continents. Yet this storm is trapped, its fury contained within the geometric walls of the hexagon, which acts like an atmospheric racetrack guiding the winds along its six-sided path. The hexagon is more than just a meteorological curiosity. It is a natural laboratory for studying physics that we cannot replicate on Earth. By observing how it changes over time, if at all, scientists can learn profound lessons about the stability of jet streams, the transition between orderly and turbulent flow, and the deep internal dynamics of gas giants. Its existence suggests that such geometric patterns might be a natural, if rare, outcome under the right conditions of rotation and wind shear, potentially occurring on other gas giants throughout the galaxy. This stunningly precise structure, a polygon etched onto a sphere of turbulent gas, serves as a powerful reminder that the laws of physics can produce order and pattern on a scale that dwarfs human imagination, creating wonders that are both mathematically elegant and awesomely powerful. And speaking of the grand, slow-motion dance of galaxies, this brings us to a fundamental number that dictates not just the fate of our local galactic neighborhood, but the ultimate destiny of the entire cosmos. This is the Hubble constant, a single, crucial value that measures the rate at which the universe is expanding. It's the speedometer of the cosmos, and right now, the readings from our most powerful instruments are telling us two different, conflicting stories. This isn't just a minor discrepancy in the data. It's a full-blown crisis in modern cosmology known as the Hubble tension, and its resolution could force us to rewrite our understanding of the universe's very foundations. The story begins nearly a century ago with the pioneering work of astronomer Edwin Hubble. By observing distant galaxies, he made the revolutionary discovery that the universe is not static, but is in fact growing larger. He noticed that the light from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. This redshift is a cosmic version of the Doppler effect. Just as the sound of a siren drops in pitch as it moves away from you, the light from a galaxy stretches to longer, redder wavelengths as it recedes from us. Hubble's genius was in realizing that the farther away a galaxy is, the faster it appears to be moving away. This relationship between distance and recessional velocity is the core of Hubble's law, and the constant of proportionality in that equation is the Hubble constant. In simple terms, it tells us how many additional kilometers per second a galaxy is moving away from us for every megaparsec of distance. A megaparsec is an astronomical unit equal to about 3.26 million light-years. So, if the Hubble constant were measured as 70 kilometers per second per megaparsec, it would mean that for every 3.26 million light-years you look out into space, galaxies are speeding away from us 70 kilometers per second faster. Determining this number with absolute precision is arguably one of the most important goals in astronomy, because it's not just about the current expansion rate. This constant is directly tied to the age of the universe. A higher expansion rate implies a younger cosmos, while a slower rate suggests an older one. More profoundly, it helps us predict the universe's final fate. Will the expansion continue forever, gradually slowing to a crawl as galaxies fade into isolation? Will it eventually reverse course in a dramatic Big Crunch? Or is dark energy, the mysterious force driving accelerated expansion, powerful enough to eventually tear the very fabric of spacetime itself? The Hubble constant is the key that unlocks these cosmic questions. The problem and the source of the current tension lies in how we measure it. Astronomers have two primary and fundamentally different methods. The first is known as the distance ladder or the local universe method. This approach builds a cosmic ladder step by step. It starts with incredibly precise measurements of distances to nearby objects like Cepheid variable stars, whose intrinsic brightness is directly linked to their pulsation period. By knowing how bright these stars truly are and comparing that to how dim they appear from Earth, we can calculate their distance with great accuracy. This first rung of the ladder calibrates the next, which might use a different kind of bright star or even thermonuclear explosions on the surface of white dwarfs. The final step involves using these calibrated distance markers to measure the distances to galaxies that host a specific type of cataclysmic explosion, a type Ia supernova. These supernovae are so brilliantly consistent in their peak brightness that they are known as standard candles. By observing these supernovae in distant galaxies, scientists can measure the universe's expansion rate directly. This meticulous, multi-step process, championed by projects like the SH0ES team, has consistently yielded a value for the Hubble constant around 73 kilometers per second per megaparsec. The second method takes a completely different approach, looking not at the relatively recent universe but all the way back to its infancy. This is the early universe method, and it relies on the afterglow of the Big Bang itself, the cosmic microwave background, or CMB. This faint radiation, which permeates all of space, is a snapshot of the universe when it was just 380,000 years old. By studying the tiny temperature fluctuations in this background haze with exquisite precision, as done by the Planck satellite, cosmologists can measure the fundamental ingredients of the early cosmos, the amounts of ordinary matter, and dark energy. They can then feed these parameters into the standard model of cosmology, known as lambda CDM, and run the clock forward 13.8 billion years to predict what the expansion rate should be today. This method produces a very confident but different value, approximately 67 kilometers per second per megaparsec. The difference between 73 and 67 might seem small, but the uncertainty in each measurement is now so incredibly tiny that the gap between them is statistically significant. They do not overlap. This is the Hubble tension. It's as if you used two different, highly accurate rulers to measure the same table and got two results that firmly disagree. This discrepancy suggests that something is fundamentally wrong. Either there is an unaccounted for error in one of the measurement techniques, which seems increasingly unlikely as both methods are refined and verified, or our standard model of cosmology is incomplete. Perhaps dark energy is not constant but evolves over time. Maybe there is a previously unknown type of neutrino or another exotic particle influencing the expansion. Or perhaps our understanding of gravity itself needs revision on the largest scales. The tension is a thrilling puzzle because it points toward new physics, a crack in our current theories through which a deeper truth might be revealed. The race is on to resolve it, using new tools like gravitational waves from neutron star collisions, which offer a completely independent way to measure cosmic distances. The outcome will not just give us a number, it will reshape our story of the universe from its fiery birth to its ultimate end. While we often think of Venus as a scorching, static world locked in a perpetual greenhouse effect, recent discoveries are revealing a planet that might be surprisingly dynamic beneath its thick, cloudy veil. For decades, Venus was considered geologically dead, a cautionary tale of a world that had baked away its internal heat long ago. But new evidence is painting a very different picture, suggesting that volcanoes on Venus are not just ancient relics. They might be active right now, potentially rewriting our understanding of the planet's hidden heart. The clues to this ongoing activity come from two main sources: direct observations of the surface showing changes over time, and the detection of mysterious, transient plumes in its atmosphere. The first compelling line of evidence comes from radar data, which is essential for piercing Venus's opaque, sulfuric acid clouds. By comparing radar maps of the same region taken years apart, scientists have spotted clear alterations to the landscape. One of the most significant findings involves a volcano called Mont Mons, one of the tallest on the planet. Images from NASA, a Magellan spacecraft in the early 1990s, showed a specific volcanic vent. When scientists analyzed data from later orbital passes, they found that this vent had visibly expanded and changed shape, strongly indicating a volcanic eruption had occurred in the interim. This wasn't a slow geological process over millions of years. This was a change that happened within a human timescale. Other studies have identified lava flows that appear fresh and unweathered by the harsh Venusian environment, suggesting they could be mere decades or centuries old, practically instantaneous in geological terms. These observations point to a world that is still being resurfaced by lava, a planet with a warm, active interior that occasionally bursts through its crust. The second, and perhaps even more tantalizing, clue comes from the atmosphere itself. The European Space Agency's Venus Express orbiter, which studied the planet from 2006 to 2015, made a puzzling discovery. It detected sudden, sharp spikes in the concentration of sulfur dioxide gas high in the Venusian atmosphere. Sulfur dioxide is a key component of volcanic emissions on Earth, and on Venus it should be quickly broken down by sunlight. Finding large, transient clouds of it suggests a recent, powerful source must be replenishing it. The most logical explanation is that a volcanic eruption injected a fresh burst of gas into the upper atmosphere. This is analogous to how a major volcanic eruption on Earth, like Mount Pinatubo, can spew sulfur dioxide high into the stratosphere, affecting global climate for years. On Venus, these gases could be acting as a tracer, a chemical signature of hidden eruptions occurring below the clouds. What does this potential for active volcanism mean for our understanding of Venus? First and foremost, it forces a major revision of the planet's geological history and internal dynamics. If Venus is still volcanically active, it means the planet has retained much more internal heat than previously believed. This heat is the engine that drives tectonic activity and volcanism. Earth stays geologically active because of heat from radioactive decay in its core and the residual heat from its formation, which is efficiently released through plate tectonics. Venus without plate tectonics must release this built-up heat in a different way, likely through episodic, massive volcanic outbursts that resurface large areas all at once. This catastrophic resurfacing model suggests that instead of a slow, steady geological cycle like Earth's, Venus might undergo planet-wide paroxysms of volcanism every few 100 million years, and the evidence of current activity implies we might be living in a quieter period between such events. But the most profound implication of active volcanoes on Venus touches on the possibility of life, albeit life of the most extreme kind. While the surface of Venus is a hellish 460 degrees Celsius, hot enough to melt lead, and has a surface pressure 92 times that of Earth, the conditions in its upper cloud decks are surprisingly temperate. At an altitude of about 50 to 60 kilometers, the temperature and pressure are remarkably similar to those on Earth's surface. Scientists have long speculated that this cloud layer could, in theory, be a habitat for airborne microbial life. Active volcanoes would provide a crucial missing ingredient for such life, a continuous supply of chemical nutrients. Volcanic eruptions would belch out not just sulfur compounds, but also water vapor and potentially other minerals and chemicals that could serve as a food source for hardy, acid-loving microbes. The plumes of volcanic gas could act as a conveyor belt, lifting nutrients from the surface into the more habitable cloud zone, creating a novel and exotic ecosystem entirely suspended in the air. This makes Venus not just a twin of Earth in size, but a world with its own hidden, potentially active, and astrobiologically fascinating environment, a place where the line between a toxic hellscape and a niche for life is thinner and more intriguing than we ever imagined. But if the hidden volcanoes of Venus hint at a dynamic world, they are built from the same familiar atoms that make up our bodies, our planet, and every star we can see. This normal matter, composed of protons, neutrons, and electrons, is everything we have ever known, touched, or observed directly, and yet it represents a mere fraction of what actually exists. This brings us to a fact so profound it completely rewrites our understanding of cosmic reality. All the stars, galaxies, planets, and interstellar gas, every single thing we can see with our most powerful telescopes accounts for just 5% of the universe. The remaining 95% is composed of two mysterious, invisible entities that we cannot see, touch, or directly detect: dark matter and dark energy. We are living in a universe dominated by forces and substances that are, for now, completely beyond our comprehension. Let's break down this cosmic recipe. Imagine the entire universe as a vast, infinite pie. If you were to slice it up, the biggest piece, a whopping 68%, would be dark energy. This is not a substance in the traditional sense, but rather a property of space itself, a mysterious force that is causing the expansion of the universe to accelerate. The next largest slice, 27%, is dark matter. This is an invisible form of matter that does not emit, absorb, or reflect any light, yet it exerts a powerful gravitational pull on the things we can see. And finally, that last tiny sliver, a mere 5%, is the ordinary matter that constitutes everything in our daily experience. This means that for over a century, our study of the cosmos has been like studying the ocean by only looking at the foam on the waves, completely missing the immense hidden depths below. The story of dark matter begins not with what we see, but with how things move. In the 1930s, a brilliant Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. He measured the velocities of individual galaxies orbiting within the cluster and made a startling discovery: they were moving far too fast. The combined gravitational pull from all the visible matter in the cluster, the stars and glowing gas, was nowhere near strong enough to hold these galaxies together. The cluster should have flown apart long ago. Zwicky concluded that there must be a huge amount of unseen matter providing the extra gravity, which he called Dunkel Materie, or dark matter. For decades, this was considered a curiosity, but the evidence became undeniable in the 1970s when astronomer Vera Rubin meticulously studied the rotation curves of spiral galaxies. She found that stars at the outer edges of galaxies were orbiting just as fast as those near the center. According to the laws of gravity, this should be impossible. The velocity should drop off with distance, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. The only explanation was that each galaxy is embedded within a gigantic, invisible halo of matter, a halo of dark matter, that extends far beyond the visible stars, providing the extra gravitational glue to keep the stars moving so quickly. So what could dark matter be? We know it's not made of atoms. It doesn't interact with light or any other part of the electromagnetic spectrum, which is why it's invisible. It also doesn't seem to interact with normal matter in any way other than through gravity. It simply passes through the Earth and even through you as if it weren't there. The leading theory is that it consists of a yet undiscovered type of elementary particle, something exotic that was created in the Big Bang. Candidates include WIMP, or weakly interacting massive particles, which are theoretical heavy particles that interact only through gravity and the weak nuclear force. Another possibility is actions, which are hypothetical extremely light particles. Decades of experiments in deep underground labs designed to shield them from cosmic rays have been trying to catch a fleeting interaction of a dark matter particle, but so far the hunt has come up empty. Its nature remains one of the greatest unsolved puzzles in physics. Then there's the even more mysterious component, dark energy. While dark matter works to pull the universe together through gravity, dark energy is doing the exact opposite. It's pushing the universe apart. The discovery was made in the late 1990s by two independent teams of astronomers who were studying distant type Ia supernova. They expected to find that the expansion of the universe was slowing down due to the collective gravitational pull of all the matter within it. Instead, they found the expansion was speeding up. It was as if you threw a ball into the air, and instead of falling back down, it shot away from you faster and faster. This shocking revelation pointed to the existence of a repulsive force that counteracts gravity on the largest scales. This force is what we call dark energy. The simplest explanation for dark energy is that it is an intrinsic property of the vacuum of space itself. According to quantum physics, empty space is not truly empty. It is a seething foam of virtual particles that constantly pop in and out of existence. This quantum froth should contain energy, and this energy of empty space could be what's causing the accelerated expansion. The problem is, when physicists try to calculate how much energy this vacuum should have, the theoretical answer is astronomically larger than what we observe, off by a factor of 10 to the power of 120. This is arguably the worst prediction in the history of science. This colossal mismatch suggests that our understanding of the quantum vacuum, or the nature of dark energy itself, is deeply flawed. Alternative theories suggest dark energy might be a dynamic field that changes over time, often referred to as quintessence, or it could even indicate that Einstein's theory of general relativity needs modification on the scale of the entire universe. The implications of this cosmic composition are staggering. Dark matter's gravitational influence was essential for the formation of galaxies and galaxy clusters in the early universe. Without its extra pull, normal matter would not have clumped together efficiently enough to form the structures we see today. Dark energy, on the other hand, dictates the universe's ultimate fate. If the acceleration continues, it points toward a cold, lonely end known as the heat death or the Big Freeze, where galaxies are pushed so far apart that the sky goes dark and star formation ceases forever. Some theories even suggest that if dark energy becomes stronger over time, it could lead to a big rip where the fabric of spacetime itself is torn apart. We are left with a humbling reality. The universe we thought we knew, the one filled with brilliant stars and majestic galaxies, is just the visible decoration on a vast, unseen framework. The true cosmic drama is being driven by dark, unknown actors, and understanding their nature is the fundamental challenge for the next generation of physicists and astronomers. And from the invisible forces that shape the cosmos, we return to our own world for a comparison that is both grounding and deeply humbling. It's a fact that connects the familiar world beneath our feet to the grand tapestry of the galaxy above, and it might just reverse your entire perspective on abundance. The number of stars in our Milky Way galaxy is almost beyond comprehension, a glittering swirl of hundreds of billions of suns. Yet, here on Earth, there are more trees than there are stars in our galaxy. Let that settle for a moment. The estimated number of stars in the Milky Way falls somewhere between 100 and 400 billion. That's a number so large we use the word billion to contain it. But the estimated number of trees on our planet is a staggering 3 trillion. That's 3,000 billion. For every single star in our vast, sprawling galaxy, there are roughly 1,000 trees right here on our own world. This astonishing figure emerged from a monumental scientific effort in 2015, when an international team of researchers combined satellite imagery with data from over 400,000 ground-based forest surveys. Before this study, rough guesses placed the global tree count at around 400 billion, which would have already been in the same ballpark as the stellar population of the Milky Way. The new, more accurate count of 3 trillion was a revelation, revealing an incredible richness of life that we had underestimated. These trees are not evenly distributed, of course. The highest densities are found in the tropical and subtropical forests, which hold about 43% of the world's trees. The boreal forests of the far north, which stretch across Russia, Canada, and Scandinavia, contain another 24%, while the temperate regions we are most familiar with account for about 22%. This means the planet's lungs are vast, but they are also concentrated in specific, often vulnerable regions. The comparison itself is a powerful tool for perspective. We look up at a clear night sky and feel small, dwarfed by the sheer number of distant suns, but this fact invites us to look around and recognize the staggering scale of our own biosphere. Our planet is teeming with life on a density that is almost unimaginable when compared to the relative emptiness of space. Each one of those 3 trillion trees is a complex, living organism, breathing in carbon dioxide, exhaling oxygen, providing habitat, stabilizing soil, and contributing to the water cycle. They are individual actors in a planetary scale system of life, a network of immense complexity and vitality. The Milky Way, for all its grandeur, is largely a collection of luminous balls of plasma separated by light years of near-total vacuum. Earth, by contrast, is a world crammed with biological activity, a vibrant oasis whose abundance is written in every leaf and root. But this perspective also comes with a profound and urgent responsibility. That 3 trillion number is not a static figure. The same study that revealed this incredible abundance also uncovered a sobering trend. Since the dawn of human civilization roughly 12,000 years ago, the total number of trees on Earth has plummeted by nearly 46%. We are currently cutting down about 15 billion trees every year, while only replanting about 5 billion. This net loss of 10 billion trees annually is a quiet crisis happening right beneath our noses. To bring the comparison full circle, the number of trees we are losing each year is a significant fraction of the entire stellar population of our galaxy. This fact transforms the statistic from a simple wonder into a call for awareness. It illustrates that the true marvel is not just the number, but the delicate balance that supports it. Our planet is a rare and precious engine of life in a cosmos that is, for the most part, silent and still. The trees stand as a testament to that miracle, and their fate is inextricably linked to our own. Just when you think the ultimate frontiers of temperature must lie in the depths of interstellar space, the universe delivers a profound irony. The coldest place we have ever discovered isn't in the shadow of a distant, dead star or in the void between galaxies. It's right here on Earth in a laboratory. For years, the title holder for the coldest natural place known was the Boomerang Nebula, a cloud of gas expanding from a dying star located about 5,000 light-years away. There, temperatures plummet to a bone-shattering 1 degree Kelvin, or minus 272 degrees Celsius, which is just a single degree above absolute zero, the theoretical point where all atomic motion ceases. That's even colder than the background glow of the Big Bang itself. But in the late 1990s, a team of scientists at the National Institute of Standards and Technology and the University of Colorado in Boulder did something extraordinary. They didn't just find a cold place, they created one, using the power of lasers to cool a cloud of rubidium atoms to a temperature that was not just a degree above absolute zero, but a mere fraction of a degree, reaching an almost unimaginable 20 billionths of a degree Kelvin above that ultimate cold. In that moment, a human laboratory on Earth became the coldest known spot in the entire cosmos. The method they used to achieve this incredible feat is as ingenious as the result itself, a technique known as laser cooling. It sounds like science fiction, but it relies on the precise application of well-understood physics. The core idea is to use the tiny pushing power of light itself to slow atoms down, because temperature, at its most fundamental level, is just a measure of how fast atoms and molecules are jiggling around. The faster they move, the hotter they are. To make something incredibly cold, you have to make its atoms almost completely still. To do this, scientists create a trap using lasers pointed at a small cloud of atoms from all directions. These lasers are meticulously tuned to a frequency just below the specific energy that the atoms would naturally absorb. Here's the clever part: because of the Doppler effect, an atom moving toward one of the laser beams will perceive that light's frequency as being slightly higher, pushing it into the range that the atom can absorb. When the atom absorbs a photon or a particle of light, it gets a tiny kick in the opposite direction, slowing it down. It then emits the photon in a random direction, and the process repeats. Since atoms are moving in every direction, they are constantly being struck by photons from the lasers opposing their motion, creating a kind of optical molasses that robs them of their speed. This slows the entire cloud, dropping its temperature to within a few thousandths of a degree above absolute zero. But the scientists in Boulder went even further, into a realm of cold so extreme that matter itself begins to behave in ways that defy our everyday experience. To reach those final, mind-boggling fractions of a degree, they used a second technique called evaporative cooling. Imagine a hot cup of coffee. The most energetic water molecules escape as steam, carrying away heat and leaving the remaining coffee cooler. The physicists did something similar with their already ultra-cold cloud of atoms. They used magnetic fields to create a trap, and then they selectively allowed the most energetic and therefore warmest atoms to escape. The atoms left behind were the slowest and coldest, and as they re-equilibrated, the entire sample's temperature plunged to just a few billionths of a degree above absolute zero. At this point, something magical happens. The atoms cease behaving as individual particles and merge into a single, unified quantum state known as a Bose-Einstein condensate. In this bizarre condition, described by the theories of Satyendra Nath Bose and Albert Einstein, millions of atoms lose their individual identities and act as one single superatom, a wave of matter that can be observed directly. It's a new fifth state of matter beyond solid, liquid, gas, and plasma. The implications of creating and studying this condensate are revolutionary. It provides a unique window into the quantum world, a realm usually hidden from view by the frantic thermal motion of particles. In a Bose-Einstein condensate, quantum effects, which normally operate on a microscopic scale, become visible to the naked eye. Scientists can observe phenomena like quantum interference and vortices that are perfect analogues to what happens in black holes and superconductors. This laboratory-made extreme cold allows us to simulate conditions that are impossible to create anywhere else, testing the fundamental laws of physics with unprecedented precision. So, while the Boomerang Nebula remains a spectacular natural example of cosmic refrigeration, its record was shattered by human curiosity and ingenuity. The coldest place in the universe is not a remote nebula. It's a small, carefully controlled chamber in a laboratory, a place where we have tamed the chaos of atoms to peer into the deepest secrets of quantum reality. But if the coldest place in the universe is a human achievement here on Earth, life itself has already accomplished something even more astonishing, proving its tenacity in the most hostile environment imaginable. We venture now from the controlled chill of the laboratory to the utter brutality of open space, where the rules for survival seem absolute and unforgiving. The vacuum is a perfect killing machine. It will suffocate you in seconds, the unshielded radiation from the sun will shred your DNA, and the temperature swings from searing heat to deep freeze would seem to destroy any complex molecule. And yet, against all odds, life has not only been exposed to this void but has come out alive on the other side. Our 27th fact reveals that certain bacteria, and perhaps the most famous extremophile of all, the tardigrade, can survive the vacuum of space, a discovery that profoundly reshapes our ideas about the limits of life and the very possibility that it could travel between worlds. Let's start with the undeniable champion of survival, the tardigrade, often affectionately called the water bear or moss piglet. These microscopic, eight-legged animals are virtually ubiquitous on Earth, found in everything from mountaintops to the deep sea. But their true superpowers are revealed when their environment turns deadly. When faced with desiccation, extreme pressure, or radiation, tardigrades don't just tough it out, they enter a state of suspended animation known as cryptobiosis. In this state, they curl into a tiny, barrel-shaped tun, expel almost all of the water from their bodies and dramatically slow their metabolism to an undetectable level, effectively pressing pause on life itself. It was this incredible ability that scientists put to the ultimate test. In 2007, the European Space Agency's Photon M3 mission carried a group of tardigrades into low Earth orbit and directly exposed them to the vacuum of space for 10 days. The results were staggering. Not only did a significant number survive the vacuum itself, but many even withstood the full blast of solar UV radiation, a dose that would be instantly lethal to almost any other known organism. Upon rehydration back on Earth, these cosmic travelers revived, went on to eat, and even reproduced normally, as if their interstellar vacation was just a minor inconvenience. But tardigrades are complex multicellular animals. Even more startling is the resilience of simple bacteria. Species like Deinococcus radiodurans have earned the nickname Conan the Bacterium for their incredible toughness. This microbe can withstand radiation doses thousands of times greater than what would kill a human, not by shielding itself, but by possessing an incredibly efficient DNA repair toolkit. Its chromosomes are arranged in a ring-like structure, and when radiation shatters its DNA into hundreds of pieces, Deinococcus simply stitches them back together correctly in a matter of hours. Experiments on the International Space Station have confirmed that colonies of these and other hardy bacteria can survive for years on the outside of the station, embedded in artificial meteorites or simply as dried-out clusters, enduring the vacuum, wild temperature swings, and constant cosmic radiation. They become dormant, waiting for conditions to improve, a strategy that could allow them to endure an interstellar journey lasting millions of years. The existence of such extremophiles provides powerful, tangible support for the ancient theory of panspermia. This is the idea that life, or at least its fundamental building blocks, might not have originated on Earth at all, but could have been delivered here from elsewhere in the cosmos, hitchhiking on comets, asteroids, or even interstellar dust grains. For a long time, a major criticism of panspermia was the sheer unlikelihood that any living thing could survive the trip. The launch from a meteorite-impacted world, the millennia-long journey through the cold, radioactive void of space, and the fiery descent through a planet's atmosphere seemed like an insurmountable chain of destructive events. The survival of tardigrades and radiation-resistant bacteria forces us to rethink each link in that chain. We now know that rocks can be ejected from planets like Mars by asteroid impacts without being fully sterilized by the shock. Simulations show that certain layers within a rock could remain cool enough to preserve life. We know that inside a sufficiently large meteorite, a smaller organism would be shielded from the worst of cosmic radiation. And we have evidence that some rocks can fall to Earth relatively gently, their descent slowed by the atmosphere without burning up completely. While we have no definitive proof that life did come to Earth this way, the experiments prove that it could have. The universe may not be a sterile void separating islands of life, but a potential transportation network with hardy microbial spores as its passengers. This discovery also forces a dramatic shift in our approach to space exploration, particularly in the field of planetary protection. Every time we send a spacecraft to another world, we risk contaminating it with earthly microbes that might have hitched a ride, no matter how rigorous our cleaning procedures. If a bacterium like Deinococcus radiodurans can survive the journey to Mars on the outside of a rover, it could potentially lie dormant in the Martian soil. This poses two major risks. First, it could completely compromise our search for alien life. If we detect life on Mars, we must be absolutely certain we aren't just detecting our own hardy stowaways. Second, and more ethically, it raises the question of whether we have a responsibility to protect potentially pristine extraterrestrial environments from terrestrial contamination. The knowledge that life can survive in space makes our robotic explorers potential and unintentional agents of panspermia, a responsibility we are only just beginning to fully appreciate. The tenacity of these earthly extremophiles shows us that the line between one world and another may be far more porous than we ever dreamed, and that life, once it arises, may possess an innate, unstoppable drive to endure and to spread. While the footprints on the moon may last for millions of years, the lunar surface itself is not as static as it appears. Our celestial companion, often thought of as a cold, geologically dead world, actually experiences its own version of earthquakes. These seismic events are called moonquakes, and they reveal a world that is still subtly active and holds surprises about its internal structure. Unlike earthquakes, which are primarily driven by the shifting of tectonic plates, moonquakes have a variety of more exotic causes, each telling a different part of the moon's story. The most powerful moonquakes originate deep within the lunar interior, hundreds of kilometers below the surface. These deep moonquakes are not random. They are meticulously predictable, tied directly to the gravitational tug of war with Earth. As our planet's gravity pulls on the moon, it stresses the lunar interior, causing it to flex slightly. This constant kneading generates these rhythmic tremors, which occur in regular cycles corresponding to the moon's orbit around Earth and its changing distance from us. The fascinating thing about these deep quakes is that they happen in specific, identified zones, suggesting the moon has a layered interior with certain structures that are more susceptible to this gravitational stressing. By studying the seismic waves from these events, scientists have been able to create a rough map of the moon's insides, revealing a core that is likely partially molten and surrounded by a thick mantle and a rigid outer crust. Far more mysterious and potentially hazardous are the shallow moonquakes. These are much less frequent but can be significantly stronger than their deep counterparts, registering up to 5.5 on the Richter scale. A quake of that magnitude on Earth would be clearly felt and could cause damage to poorly constructed buildings. Their origin is still not fully understood, but the leading theory points to tectonic activity. Yes, the moon, without plate tectonics, still has a crust that is adjusting and cracking under global stresses. These stresses could be the result of the moon's ongoing cooling and contraction, a process we also see on Mercury. As the interior cools, the crust shrinks and cracks, releasing built-up strain in sudden, powerful slips along faults. The energy from these shallow moonquakes can reverberate through the lunar crust for an astonishingly long time, sometimes over 10 minutes, because the moon's dry, rigid rock transmits seismic waves far more efficiently than Earth's fractured, water-soaked crust. For future lunar colonists, understanding these shallow moonquakes will be critical for designing structures that can withstand these long-lasting tremors. Then there are the two more gentle and much more frequent types of lunar shaking. Thermal moonquakes are a direct result of the moon's extreme temperature swings. As the lunar surface moves from 2 weeks of blistering sunlight, where temperatures soar to 120 degrees Celsius, into 2 weeks of deep, shadowed night, where temperatures plummet to -130 degrees Celsius, the rock itself expands and contracts. This daily, or rather fortnightly, thermal stress causes the surface to crack and pop, creating tiny, predictable tremors every sunrise and sunset. Finally, the moon is constantly bombarded by meteoroids. These impacts, ranging from tiny dust-sized particles to larger rocks, create their own distinct seismic signals. The Apollo astronaut seismometers recorded thousands of these impact events, each one a tiny hammer tap helping scientists chart the population of small objects zipping around in near-Earth space. The data for all of this comes from the incredibly successful Apollo passive seismic experiment. Between 1969 and 1977, the Apollo missions placed 4 sophisticated seismometers at different landing sites, creating a network that recorded over 13,000 seismic events. This treasure trove of data is what planetary scientists still use today to understand the moon's inner workings. The discovery of moonquakes completely overturned the idea of a completely dead moon. It showed us that our companion is a dynamic world with a complex internal structure, still feeling the gravitational embrace of Earth and slowly settling and cooling from its formation over 4.5 billion years ago. For future exploration, this knowledge is not just academic. It's a vital safety manual revealing a world that occasionally rumbles and shakes, a subtle reminder that even in the quiet of space, nothing is ever perfectly still. But this gradual cooling of the moon and the faint tremors that ripple through its crust are powered by a distant, brilliant engine that is itself undergoing a constant and staggering transformation. We've talked about the Sun's paradoxical hot atmosphere and its magnetic mysteries, but its most fundamental and relentless process is happening deep within its core, a furnace so powerful that it is quite literally consuming the star from the inside out. Our Sun, the steady anchor of our solar system, is losing mass at an almost incomprehensible rate. Every single second, our star sheds approximately 4 million tons of its substance, vanishing into pure energy. To put that into a more tangible scale, that's the equivalent of the mass of a large pyramid disappearing every second. This isn't a slow leak. It's a continuous, titanic conversion that has been running for billions of years and dictates the ultimate fate of every planet that orbits it. The mechanism behind this staggering mass loss is the very same process that gives the Sun its light and warmth: nuclear fusion. At the star's incredibly dense and hot core, where temperatures soar to over 15 million degrees Celsius and pressures are immense, hydrogen atoms are forced together with such violence that they overcome their natural electromagnetic repulsion and fuse to create helium. This fusion reaction is not a simple one-to-one swap, however. If you were to take 4 hydrogen nuclei, each consisting of a single proton, and fuse them into one helium nucleus, which has 2 protons and 2 neutrons, you would find that the resulting helium atom has slightly less mass than the 4 hydrogen atoms you started with. A tiny fraction of the original mass, about 0.7%, has simply vanished. But according to Albert Einstein's most famous equation, E equals mc squared, mass and energy are 2 sides of the same coin. That lost mass hasn't disappeared. It has been transformed into a staggering amount of energy. The c in that equation represents the speed of light, a number so enormous that when you square it, it becomes a multiplier of almost unimaginable scale. This means that converting even a minuscule amount of mass releases a colossal amount of energy. The 4 million tons of mass the Sun loses every second is the fuel for the energy output that has sustained life on Earth for eons. This process is the ultimate example of cosmic efficiency. Every photon of sunlight that warms your skin, every beam that fuels photosynthesis in a leaf, is a direct product of this mass energy conversion happening 150 million kilometers away. The sunlight you see today began its journey as energy in the solar core tens of thousands of years ago, spending most of that time bouncing randomly between atoms in a slow, zigzagging path called the radiative zone before reaching the convective zone and finally racing through space to reach us in just over 8 minutes. The sheer scale of this engine is what allows it to sustain such a phenomenal loss. The Sun's total mass is a whopping 2 billion tons. So, while 4 million tons per second sounds catastrophic, it represents only a tiny fraction of the Sun's total bulk. Over its entire 10 billion-year main sequence lifespan, the Sun will have converted only about 0.1% of its initial mass into energy. It's a testament to the sheer immensity of a star that it can afford to be so prodigal with its substance for so long. Yet, this constant shedding of mass has subtle but profound long-term consequences for the entire solar system. Because the Sun's gravitational grip on the planets is directly proportional to its mass, as the Sun gets lighter, its gravitational pull weakens ever so slightly. This causes the planets to slowly spiral outward into larger orbits. The effect is minuscule on human timescales. Earth's orbit is expanding by about 1.5 centimeters per year, but over billions of years, this contributes to the grand, slow-motion dance of the solar system. More importantly, this mass loss is the timer counting down to the Sun's demise. The Sun is not an infinite fuel source, it is a finite reservoir of hydrogen. As it continues to fuse hydrogen into helium in its core, it is gradually building up a central ash of helium that cannot yet be fused because the core isn't hot or dense enough. In about 5 billion years, the hydrogen in the core will be depleted, ending the main sequence phase. This will trigger a series of dramatic events. The core will contract and heat up, eventually igniting helium fusion in a violent flash called the helium flash, while the outer layers will expand hundreds of times, engulfing the inner planets and transforming the Sun into a red giant. The steady, silent loss of mass we see today is the quiet, patient ticking of that cosmic clock, a reminder that even the most constant presence in our sky is on a journey with a definitive end, its light powered by its own slow and magnificent consumption. And from the steady, predictable consumption of our Sun, we arrive at the final and perhaps most mind-bending frontier of all, a concept that challenges the very meaning of reality itself. Throughout our journey, we've explored the bizarre and the wonderful, from diamond planets to invisible matter. But our 30th fact ventures into the realm of the profound, a theoretical possibility that sounds like it's straight out of the most ambitious science fiction. There might be an entire mirror universe, a cosmic reflection of our own where time runs backwards. This isn't just a wild guess. It's a serious, though highly speculative, idea that emerges from one of the most fundamental and successful theories in all of physics, the Standard Model of particle physics. This model describes the behavior of all known subatomic particles and forces with breathtaking accuracy, and at its heart lies a principle known as CPT symmetry. CPT stands for charge, parity, and time. Let's break that down. Charge reversal means swapping every particle with its antiparticle, turning an electron into a positron, for example. Parity reversal is like looking at the universe in a mirror, so left becomes right and right becomes left. And time reversal means exactly what it sounds like, running the clock backwards. According to our best theories, the laws of physics should be perfectly symmetric under the combined application of all three of these reversals. If you were to take the entire universe and simultaneously flip the charge of every particle, view it in a mirror, and run time backwards, the resulting cosmos would obey exactly the same physical laws as our own. It would be, from a fundamental physics perspective, completely valid and indistinguishable in its rules of operation. This CPT symmetry is considered sacred. No experiment has ever violated it. Now, here's where the leap to a mirror universe happens. Our observable universe, the one we live in, is not perfectly symmetric under these individual operations. For instance, time has a very clear direction for us. We remember the past, not the future. Eggs scramble, but they don't unscramble. This is known as the arrow of time, largely driven by the second law of thermodynamics and the increase of entropy or disorder. But if CPT symmetry must hold true, and our universe clearly has a preferred direction for time, some physicists like Nobel laureate Roger Penrose have pondered a radical solution. What if the reason we perceive this asymmetry is because we are only seeing one half of the full picture? What if the Big Bang didn't just create our universe, but it also created a perfect CPT mirror image of it? In this hypothetical scenario, the mirror universe would be a direct consequence of applying the CPT operation to our own. In that cosmos, everything would be reversed. Particles would be antiparticles, the chirality or handedness of molecules would be flipped, and crucially, the arrow of time would point in the opposite direction. From our perspective, time in that universe would be flowing backwards, but here's the essential point. From the perspective of an observer in that universe, their experience would feel perfectly normal. They would perceive their past as our future and our future as their past to them. Our universe would be the one where time runs backwards. each universe would see the other as impossibly strange, while feeling their own flow of time as the natural and forward-moving one. This idea provides a beautifully elegant solution to a profound mystery. Why did the Big Bang have such a low entropy? The universe began in a state of incredibly high order and has been evolving towards disorder ever since, which gives us our arrow of time. A CPT symmetric cosmology would explain this by suggesting that the Big Bang was actually the point of maximum entropy, the central moment from which two universes emerged, each moving forward in their own perceived time, increasing in entropy away from that common origin. It would mean that the ultimate fate of our universe, perhaps a heat death of maximum disorder, is, from the mirror universe's point of view, the Big Bang itself. Of course, this remains a highly speculative theory. We have no way to observe or interact with this mirror universe, as it would exist as a separate reality. But the fact that such a profound and strange idea emerges naturally from our most fundamental understanding of physics is a testament to the depth of the mysteries we are still unraveling. It suggests that our reality, for all its concrete feel, might be just one facet of a far grander, more symmetric structure, a cosmic dance of creation and dissolution where the concepts of before and after are merely a matter of perspective. And so, our journey through the cosmos comes to a close for now. We've traveled from the slow retreat of our own moon to the hypothetical shores of a mirror universe where time flows in reverse. We've witnessed diamonds the size of planets, smelled the pungent aroma of ancient comets, and learned that the very ground we stand on is more abundant with life than all the stars in our galaxy. Each of these 30 facts serves as a powerful reminder that the universe is not the tidy, predictable place we learned about in school. It is a realm of magnificent extremes, profound mysteries, and constant dynamic change. The serene night sky is a veil, and behind it lies a reality of unimaginable violence, beauty, and complexity that is only just beginning to reveal itself to our curious minds. The most astonishing revelation of all, perhaps, is not any single fact, but the recurring theme that humbles our understanding. We discovered that the matter we can see and touch makes up a mere 5% of the cosmos, with the rest governed by dark, enigmatic forces we cannot yet explain. We found that even the most permanent-seeming features, like Jupiter's Great Red Spot, are transient on a cosmic scale, and that planets can be orphaned, wandering the eternal night between stars. This journey underscores a fundamental truth. For every question we answer, the universe presents 10 more. The edge of our knowledge is not a final frontier, but a horizon that continuously expands the further we travel. We are like explorers who have just mapped the coastline of a vast, uncharted continent, aware that the true wonders lie deep in the interior, waiting to be discovered. This is where you come in. The story of the universe is not just for astronomers in observatories. It's a story that belongs to all of us, to anyone who has ever looked up at the stars and felt a sense of wonder. I'm incredibly curious to know which of these facts reshaped your perspective the most. Was it the touch temperature brown dwarfs, the hidden water ice on Mercury, or the eerie, singing magnetic fields of our own planet? Let's continue this conversation down in the comments. Share your favorite cosmic revelation and tell me what it made you think about. Your thoughts and curiosity are what make exploring these mysteries so rewarding. If this journey into the unknown has sparked your imagination, just remember that this is only the beginning. The cosmos is filled with countless more secrets waiting to be uncovered, from the nature of dark matter to the potential for life on distant moons. If you don't want to miss our next adventure into the great mysteries of space, make sure to hit that subscribe button and ring the notification bell. There is always more to explore, more to question, and more to wonder at. Thank you for joining me on this voyage beyond the textbook. Keep looking up, stay curious, and never stop wondering about the incredible universe we call